Imagine if every moment you blinked, the world around you shifted from a haze of endless possibilities to one clear, definite reality. Picture a universe where nothing is fixed until someone, even you, looks at it. It sounds like something out of a science fiction thriller, yet this is the bizarre premise at the heart of the quantum measurement problem. Today, we're diving into a concept that suggests our act of observing could be what gives the universe its shape, turning fuzzy probabilities into the solid reality we experience. At its core, the quantum measurement problem arises from the strange behavior of particles at the quantum level. In the quantum world, particles such as electrons and photons don't exist in a single, determined state. Instead, they reside in a mysterious condition known as superposition, a blend of all possible states at once. Think of it as a cosmic coin spinning in the air, where heads and tails coexist until it finally lands. This peculiar behavior is described by something called the wave function, a mathematical tool that outlines all the possible states of a particle. However, as soon as we measure or observe this particle, the wave function collapses and the particle snaps into one definite state. It's as if the universe holds its breath until we intervene, then it rushes to pick a single, concrete outcome. Consider the famous double-slit experiment. When particles pass through two slits without any observation, they create an interference pattern, proof that they behave like waves. But when we set up detectors to see which slit each particle goes through, the interference pattern vanishes. Suddenly, they act like solid particles following a definite path. This experiment hints at a strange relationship between the act of measurement and the nature of reality itself. Now, let's delve into two of the most talked about interpretations of this phenomenon. The first is the Copenhagen interpretation. This view suggests that the wave function represents our knowledge of a quantum system rather than a physical reality. According to this perspective, the act of measurement forces the system to choose one of the many possibilities, causing the wave function to collapse. It paints a picture of the observer as an almost magical participant who brings the world into clarity simply by looking. On the flip side, we have the many worlds interpretation. This theory boldly claims that every potential outcome of a quantum event actually happens, but in separate, parallel universes. Instead of a wave function collapse, the universe splits into multiple realities, each embodying a different outcome. In this view, our measurement doesn't force a single decision. It just determines which branch of the multiverse we find ourselves in. This idea challenges our traditional view of a single, linear reality, suggesting instead an endless, branching tree of possibilities. Both interpretations offer fascinating insights into the nature of quantum reality, yet they stand in stark opposition. The Copenhagen interpretation emphasizes the mysterious power of observation, suggesting that our very act of looking defines reality. In contrast, the many worlds interpretation minimizes the role of the observer, positing that all outcomes exist simultaneously in an ever-expanding cosmos of parallel universes. In wrapping up our journey through the quantum measurement problem, we are left with an awe-inspiring puzzle that straddles the line between science and philosophy. Whether reality truly hinges on our observation, or if our universe is merely one branch of a vast multiverse, the debate continues to challenge our understanding of existence. What is clear, however, is that the quantum world invites us to question everything we think we know about reality. By exploring these ideas, we not only gain insights into the fabric of the universe, but also learn to appreciate the inherent mysteries that make life so intriguing. In the end, the quantum measurement problem reminds us that the universe might be far more fluid and enigmatic than our everyday experiences suggest, an invitation to continually explore, question, and marvel at the unknown. Imagine watching a film where shattered glass leaps off the floor, reassembling into a perfect window, or where smoke funnels back into a chimney. Such scenes defy our everyday experience, yet the fundamental laws of physics don't explicitly forbid them. This leads us to a profound enigma. Why does time seem to flow inexorably in one direction, from past to future, when theoretically it could just as easily run backward? This is the essence of the arrow of time paradox, a concept that challenges our understanding of reality and the very nature of existence. The term arrow of time was introduced by British astrophysicist Arthur Eddington in 1927 to describe the unidirectional flow of time that we perceive. While the fundamental laws governing microscopic particles are time-symmetric, meaning they don't prefer a forward or backward direction, our macroscopic world exhibits a clear temporal asymmetry. This discrepancy forms the crux of the paradox. One of the most compelling explanations for this phenomenon lies in the second law of thermodynamics, which states that entropy, a measure of disorder in a system, tends to increase over time. In simple terms, natural processes evolve from a state of order to disorder. For instance, a hot beverage cools down as heat dissipates into the surrounding air, and a deck of cards, once shuffled, is unlikely to return to its original ordered state without deliberate intervention. This progression from order to disorder gives rise to the thermodynamic arrow of time, aligning the direction of time with the increase of entropy. However, this explanation raises further questions. If the laws of physics are time-symmetric, why does entropy increase at all? Some physicists propose that the initial conditions of the universe play a pivotal role. They suggest that the universe began in a highly ordered, low-entropy state, a cosmic starting point that set the direction for the arrow of time. As the universe expands and evolves, entropy increases, creating the temporal asymmetry we observe. Yet, not all scientists agree with this perspective. Some argue that our perception of time's flow is a construct of human consciousness, a way for our brains to process and organize information. This viewpoint suggests that the arrow of time is not an inherent feature of the universe, but rather a byproduct of how we experience and interpret reality. The arrow of time paradox invites us to ponder the profound nature of time and our place within it. Whether rooted in the fundamental laws of physics, the initial conditions of the cosmos, or the workings of our consciousness, the unidirectional flow of time remains one of the most intriguing mysteries in science. As we continue to explore this enigma, we not only deepen our understanding of the universe, but also challenge our perceptions of reality, causality, and existence itself. Imagine gazing up at the night sky, each twinkling star potentially hosting planets teeming with life. With billions of stars in our galaxy alone, it's statistically probable that intelligent civilizations should exist elsewhere. Yet, despite our best efforts, we find ourselves in a profound silence. This puzzling contradiction between the high likelihood of extraterrestrial intelligence and the lack of evidence for its existence is known as the Fermi Paradox, a question that challenges our understanding of our place in the cosmos. The Fermi Paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox arises from two observations. The vastness of the universe suggests that intelligent life should be common, yet we have no definitive proof of such life beyond Earth. This discrepancy has led to numerous hypotheses attempting to explain the silence. One prominent explanation is the concept of the Great Filter, which suggests that there is a stage in the evolutionary timeline that is extremely difficult for life to surpass. This filter could be behind us, implying that the emergence of intelligent life is rare, or ahead of us, indicating that advanced civilizations tend to self-destruct before achieving interstellar communication. The Great Filter thus presents a sobering perspective on the longevity of technological societies. Another consideration is the possibility that advanced civilizations are utilizing communication methods beyond our current technological capabilities. While humanity primarily searches for radio signals, extraterrestrial societies might employ more sophisticated means, such as neutrino-based communication or quantum entanglement, rendering their messages undetectable by our instruments. The zoo hypothesis offers a different angle, proposing that advanced civilizations intentionally avoid contact with us to allow for natural evolution and socio-cultural development, much like zookeepers observing animals without interference. This perspective suggests that Earth is part of a cosmic preserve, shielded from interaction until we reach a certain level of maturity or technological prowess. Alternatively, the planetarium hypothesis posits that our perception of the universe is a carefully crafted illusion designed to appear empty of other life. In this scenario, advanced beings have created a simulated reality for us, and the true nature of the cosmos, including the existence of other civilizations, remains hidden behind this facade. Some theories suggest that extraterrestrial civilizations are indeed out there, but are simply uninterested in communication or exploration. They may be content with their own environments, lacking the curiosity or motivation to seek out other life forms. Additionally, the vast distances between stars present significant challenges for interstellar travel and communication, potentially leading civilizations to focus inward rather than outward. The Fermi Paradox encapsulates the profound mystery of our solitude in the vast expanse of space. Whether the silence signifies the rarity of intelligent life, the limitations of our detection methods, or the presence of insurmountable barriers, it compels us to reflect on our own civilization's trajectory and the future of our exploration efforts. As we continue to scan the cosmos for signs of life, the paradox serves as a humbling reminder of the challenges inherent in our quest to understand our place in the universe. Imagine for a moment that everything you know, your memories, your experiences, your very existence, is an illusion. What if you are nothing more than a fleeting, self-aware entity that spontaneously materialized from the chaotic void of the universe, complete with fabricated memories and perceptions? This unsettling thought experiment is at the heart of the Boltzmann brain paradox, a concept that challenges our understanding of reality, consciousness, and the nature of the universe itself. The Boltzmann brain paradox is rooted in the principles of thermodynamics and statistical mechanics, disciplines that study the behavior of systems with a large number of particles. In the late 19th century, Austrian physicist Ludwig Boltzmann sought to explain the apparent order and low entropy, a measure of disorder, observed in the universe. He proposed that the universe, over vast periods, naturally fluctuates between states of high and low entropy due to random thermal motions of particles. Occasionally, these fluctuations could lead to the spontaneous formation of ordered structures, such as stars, planets, or even conscious beings. Building upon Boltzmann's ideas, the paradox suggests that it is statistically more probable for a single self-aware entity, a Boltzmann brain, to emerge from random fluctuations than for an entire universe like ours to exist. This is because the spontaneous assembly of a solitary brain requires far fewer particles and a smaller decrease in entropy compared to the formation of a vast, organized cosmos. Consequently, if the universe were eternal and infinite, we would expect Boltzmann brains to vastly outnumber normal observers like ourselves. This leads to a profound philosophical dilemma. If Boltzmann brains are the most common form of consciousness in the universe, how can we be certain of our own experiences and perceptions? Could we be Boltzmann brains, spontaneously arisen with fabricated memories and sensations, existing momentarily before dissolving back into the cosmic chaos? This scenario challenges the very foundation of empirical knowledge and raises questions about the reliability of our observations and the scientific method. The Boltzmann brain paradox also intersects with modern cosmological theories, particularly those concerning the nature of the universe's expansion and the concept of the multiverse. Some cosmologists argue that in a universe undergoing eternal inflation, a state of perpetual exponential expansion, pocket universes with varying physical laws could emerge. Within this framework, the likelihood of Boltzmann brains appearing becomes a significant concern, as their prevalence could undermine the assumption that our observations reflect an objective external reality. To address this paradox, scientists have proposed several resolutions. One approach involves re-examining the assumptions about the universe's initial conditions and the mechanisms governing entropy. If the universe began in a state of exceptionally low entropy, the subsequent evolution could favor the emergence of complex structures and conscious beings like ourselves over Boltzmann brains. Another perspective suggests that our very ability to question our existence and observe the universe implies a level of coherence and continuity incompatible with the fleeting nature of Boltzmann brains. The Boltzmann brain paradox serves as a profound reminder of the complexities inherent in understanding consciousness, reality, and the cosmos. It challenges us to critically examine the assumptions underlying our perception of existence and the methodologies we employ to explore the universe. While the notion that we might be ephemeral, spontaneously formed brains is deeply unsettling, it also underscores the importance of continued inquiry and the pursuit of knowledge. By confronting such paradoxes, we not only deepen our comprehension of the universe, but also enrich our appreciation for the mysteries that define our place within it. Imagine a cosmic shredder, a region in space so dense and powerful that it swallows everything in its vicinity, including light, and seemingly erases any trace of their existence. This is the enigmatic nature of black holes. Yet, a profound question arises: does the information about the swallowed matter truly vanish forever? This conundrum, known as the black hole information paradox, challenges our fundamental understanding of physics and the nature of reality. The paradox stems from a clash between two pillars of modern physics, quantum mechanics and general relativity. Quantum mechanics asserts that information about a physical system's state cannot be destroyed. In contrast, general relativity predicts that anything crossing a black hole's event horizon is lost to the universe, leading to a potential violation of information conservation. In 1976, physicist Stephen Hawking introduced the concept of Hawking radiation, suggesting that black holes emit radiation due to quantum effects near the event horizon. Over time, this radiation could cause black holes to evaporate completely. However, Hawking proposed that this radiation is thermal and lacks information about the black hole's interior, implying that information about the infalling matter is irretrievably lost, a proposition that contradicts the principles of quantum mechanics. This paradox has spurred numerous theoretical developments. One significant advancement involves the calculation of the von Neumann entropy of Hawking radiation. Recent studies have shown that, in specific models of quantum gravity, the entropy of this radiation first rises and then falls back to zero, aligning with the predictions of unitary evolution in quantum mechanics. These findings suggest that information is not lost but rather encoded in the radiation, offering a potential resolution to the paradox. Another intriguing approach involves the concept of replica wormholes, novel configurations in spacetime that contribute to the entropy calculations of Hawking radiation. The inclusion of these wormhole geometries prevents the entropy from increasing indefinitely, indicating that information may be preserved and accessible in principle. Additionally, some researchers propose that information is always available outside the black hole, challenging the assumption that the exterior region has no information about its interior. This perspective implies that the von Neumann entropy of the region outside the black hole remains zero, suggesting that information is not lost but can be recovered through precise measurements. The black hole information paradox remains a profound puzzle at the intersection of quantum mechanics and general relativity. While recent theoretical advancements offer promising avenues toward its resolution, the paradox continues to challenge our understanding of the universe's fundamental laws. As we delve deeper into the mysteries of black holes, we inch closer to uncovering the true nature of information, reality, and the cosmos itself. Imagine a force so subtle yet so pervasive that it dictates the very fabric and fate of our universe. This force, known as the cosmological constant, is believed to be responsible for the accelerated expansion of the cosmos. However, our theoretical predictions of its value are astoundingly different from what we observe, a discrepancy so vast that it's often dubbed the worst theoretical prediction in the history of physics. This conundrum is the essence of the cosmological constant problem, a puzzle that challenges our deepest understanding of physics and the universe. The cosmological constant, denoted by the Greek letter lambda, was initially introduced by Albert Einstein in 1917 as a modification to his equations of general relativity. At the time, it was intended to allow for a static universe, counteracting the attractive force of gravity. However, after the discovery that the universe is expanding, Einstein reportedly referred to the cosmological constant as his biggest blunder. Ironically, decades later, observations of distant supernovae in the late 1990s revealed that not only is the universe expanding, but this expansion is accelerating, suggesting the presence of a repulsive force, now associated with the cosmological constant or dark energy. The crux of the cosmological constant problem lies in the staggering discrepancy between theoretical predictions and observational measurements. Quantum field theory, QFT, which successfully describes the behavior of fundamental particles, predicts a vacuum energy density, a manifestation of the cosmological constant that is about 120 orders of magnitude larger than what we observe. This means that the theoretical value is a factor of 10 superscript 1 superscript 2 times greater than the measured value, leading to a profound and unresolved conflict between theory and observation. Several approaches have been proposed to address this problem. Modified theories of gravity. Some physicists suggest altering Einstein's general relativity to account for the observed acceleration without invoking a cosmological constant. However, these modifications often struggle to align with the precision of current experimental data. Anthropic principle and the multiverse. This perspective posits that the cosmological constant's value is not determined by fundamental physics alone, but varies across a vast multiverse. In regions where lambda is too large or too small, galaxies and life as we know it couldn't exist. Therefore, we find ourselves in a universe with a cosmological constant conducive to our existence, a selection effect known as the anthropic principle. Dynamic dark energy, quintessence, instead of a constant lambda. Some theories propose a dynamic field that evolves over time, known as quintessence. This approach suggests that the energy driving cosmic acceleration changes, potentially aligning theory with observations. Vacuum energy cancellation mechanisms. Certain models explore mechanisms where contributions to vacuum energy cancel out, resulting in the small observed value of the cosmological constant. These theories are still in development and require further exploration. Despite extensive efforts, a definitive solution to the cosmological constant problem remains elusive. It stands as a profound challenge at the intersection of quantum mechanics, general relativity, and cosmology, highlighting the limitations of our current theoretical frameworks. The cosmological constant problem serves as a humbling reminder of the vast unknowns that still pervade our understanding of the universe. It underscores the need for innovative thinking and novel approaches to reconcile the discrepancies between theory and observation. As we continue to probe the cosmos and refine our theories, this enigma remains a beacon, guiding physicists toward a deeper comprehension of the fundamental laws governing reality. Imagine two particles, once intertwined in the mysterious dance of quantum entanglement, now separated by vast cosmic distances. Yet an instantaneous change in one seemingly affects the other, defying our classical notions of space and time. This phenomenon, at the heart of the Einstein-Podolsky-Rosen (EPR) paradox, challenges our understanding of reality and locality, propelling us into the perplexing realm of quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a thought-provoking paper titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" Wikipedia. They introduced a thought experiment involving two particles in a shared quantum state, such that measuring a property, like position or momentum, of one particle instantaneously determines the corresponding property of the other, regardless of the distance separating them. This led to the concept of elements of reality, physical quantities whose values can be predicted with certainty without disturbing the system. Einstein and his colleagues argued that this instantaneous correlation implied that quantum mechanics was incomplete, suggesting the existence of hidden variables, unknown parameters that could account for these correlations without invoking spooky action at a distance. They believed that a more complete theory, adhering to the principles of locality, no faster-than-light interactions, and realism, physical properties exist prior to measurement, was necessary to fully describe physical reality. However, in 1964, physicist John Bell formulated what is now known as Bell's theorem, providing a way to test the validity of local hidden variable theories. Bell derived inequalities, mathematical constraints, that any local realistic theory must satisfy. Quantum mechanics, however, predicts violations of these inequalities under certain conditions. Subsequent experiments have consistently observed violations of Bell's inequalities, supporting the non-local predictions of quantum mechanics and challenging the notion of local realism. This experimental evidence implies that either locality or realism, or both, must be abandoned, leading to profound philosophical debates about the nature of reality. Quantum non-locality suggests that entangled particles are connected in such a way that the state of one instantaneously influences the state of the other, irrespective of the distance between them. This phenomenon has been experimentally verified through various tests, including those addressing potential loopholes, further solidifying the non-local character of quantum mechanics. The EPR paradox and the concept of quantum non-locality have not only deepened our understanding of quantum mechanics, but have also paved the way for technological advancements. Quantum entanglement, once considered a peculiar theoretical construct, is now harnessed in emerging fields like quantum computing and quantum cryptography, promising unprecedented computational power and secure communication methods. The EPR paradox serves as a profound reminder of the counterintuitive nature of the quantum world, challenging our classical intuitions about separability and locality. As we continue to explore the depths of quantum mechanics, we are compelled to rethink our notions of reality and embrace the enigmatic interconnectedness that defines the quantum realm. Imagine gazing into the vast expanse of the cosmos, only to realize that everything we see, stars, planets, galaxies, accounts for a mere fraction of the universe's total mass. An unseen entity, known as dark matter, constitutes approximately 85% of all matter in the universe, yet it neither emits nor absorbs light, rendering it invisible and undetectable by conventional means. This profound mystery, often referred to as the dark matter paradox, challenges our understanding of the universe's composition and the fundamental laws governing it. The existence of dark matter was first postulated in the early 20th century when astronomers observed gravitational effects that couldn't be explained by visible matter alone. For instance, the rotational speeds of galaxies and the behavior of galaxy clusters suggested the presence of unseen mass exerting gravitational influence. Despite extensive efforts, dark matter has eluded direct detection, deepening the enigma surrounding its nature. Several hypotheses have emerged to explain this cosmic puzzle. Weakly interacting massive particles. These are theoretical particles that interact via gravity and possibly the weak nuclear force, but not electromagnetically, making them difficult to detect. Numerous experiments have sought WIMPs, but definitive evidence remains elusive. Modified gravity theories. Some scientists propose that our understanding of gravity might be incomplete, suggesting modifications to Newtonian dynamics or general relativity. Theories like modified Newtonian dynamics (MOND) attempt to account for galactic rotation curves without invoking dark matter. However, these theories face challenges in explaining all observed phenomena. Primordial black holes. Another proposition is that dark matter consists of black holes formed in the universe's infancy. While intriguing, this hypothesis requires further investigation to reconcile with observational data. Recent observations have added layers to this paradox. For instance, discrepancies in the clumpiness of dark matter have been noted. Astrophysicists measured this clumpiness to be 0.76, conflicting with the cosmic microwave background value of 0.83, indicating possible errors or an incomplete cosmological model. Moreover, the James Webb Space Telescope has confirmed that the universe is expanding at a rate about 8% faster than expected, a phenomenon known as the Hubble tension. This discrepancy suggests a gap in our current understanding of the universe, particularly concerning dark matter and dark energy, which constitute 96% of the cosmic makeup. These inconsistencies have led some researchers to question the very existence of dark matter. Alternative theories propose that the phenomena attributed to dark matter might instead result from unknown aspects of gravity or other fundamental forces. However, these theories face challenges in explaining the full range of observational evidence. The dark matter paradox stands as one of the most profound mysteries in modern astrophysics, challenging our understanding of the universe's composition and the laws governing it. As researchers continue to explore this enigma through observations and theoretical models, each discovery brings us closer to unraveling the secrets of the cosmos. Embracing this mystery not only deepens our appreciation for the universe's complexity, but also fuels the quest for knowledge that drives scientific inquiry. Imagine standing at the edge of a vast chasm, peering into the abyss, and wondering how such a profound gap came to be. In the realm of physics, this chasm exists between two fundamental scales, the Planck scale, where gravity reigns supreme, and the electroweak scale, governing the behavior of the Higgs boson and the weak force. The staggering disparity between these scales poses a profound puzzle, known as the hierarchy problem, challenging our understanding of the universe's fundamental laws. The hierarchy problem centers on the question: why is the weak force responsible for processes like radioactive decay so much stronger than gravity? This discrepancy becomes particularly puzzling when considering the mass of a Higgs boson, the particle associated with the Higgs field that imparts mass to other particles. Quantum corrections suggest that the Higgs mass should be much larger than observed unless there is an extraordinary degree of fine-tuning, a delicate balancing act between large numbers that cancels out these corrections. This fine-tuning appears unnatural and begs for a deeper explanation. The problem is not merely academic, it has practical implications for our understanding of the universe. For instance, the vast difference in strength between the weak force and gravity influences the behavior of stars, the formation of galaxies, and the evolution of the cosmos itself. Addressing the hierarchy problem could shed light on why the universe is structured the way it is, and whether there are deeper symmetries or principles yet to be discovered. Over the decades, physicists have proposed various solutions to this conundrum. One such approach involves the concept of supersymmetry, which posits a relationship between two basic classes of particles, bosons and fermions. Supersymmetry aims to address the hierarchy problem by introducing new particles that could cancel out the quantum corrections affecting the Higgs mass. However, despite extensive searches, no experimental evidence for supersymmetric particles has been found, leaving this solution in the realm of speculation. Another intriguing proposal involves the idea of extra dimensions. In this framework, our familiar three-dimensional space is augmented by additional spatial dimensions that are compactified or curled up at scales beyond current observational capabilities. The existence of these extra dimensions could provide a natural explanation for the weakness of gravity compared to other forces. By distributing gravitational strength across these extra dimensions, gravity's relative weakness in our observable universe could be understood. However, this hypothesis also faces challenges, particularly in reconciling with existing experimental data. The hierarchy problem also intersects with cosmological considerations. The cosmological constant problem, which questions why the energy density of the vacuum is so small yet non-zero, also points to a potential connection between quantum field theory and general relativity. Understanding how these vast differences in energy scales arise could provide insights into both the large-scale structure of the universe and the fundamental laws governing particle interactions. The hierarchy problem stands as a testament to the complexities and mysteries that permeate the fabric of our universe. It challenges physicists to look beyond the established theories and venture into realms that may fundamentally alter our understanding of reality. As research continues, each hypothesis and experiment brings us closer to unraveling the true nature of the forces that govern the cosmos, potentially leading to a more unified and profound comprehension of the laws of physics. Imagine possessing the ability to traverse the corridors of time, journeying to eras long past or distant futures. While this concept has captivated human imagination for centuries, it also gives rise to perplexing conundrums that challenge our understanding of causality and existence. Two of the most intriguing are the grandfather paradox and the Bootstrap paradox, both of which underscore the complexities inherent in the notion of time travel. The grandfather paradox, a twist in the fabric of causality. The grandfather paradox presents a scenario where a time traveler journeys to the past with the intent to prevent their own existence. A classic illustration involves a traveler who goes back in time and inadvertently causes the death of their grandfather before the traveler's parent is conceived. This act would render the traveler's birth impossible, creating a logical contradiction. If the traveler was never born, how could they have traveled back in time to commit the act? This paradox challenges our conventional understanding of cause and effect, suggesting that altering past events could lead to self-contradictory outcomes. While some theories propose that such paradoxes could be resolved through mechanisms like parallel universes or self-consistency principles, no definitive solutions have been universally accepted. The Bootstrap Paradox, the enigma of self-causation. The Bootstrap Paradox, also known as an ontological paradox, involves a scenario where an item or piece of information exists without a clear point of origin, creating a causal loop that defies logical explanation. A popular example is the story of a time traveler who gives Shakespeare a copy of his own works. Shakespeare publishes them, and the time traveler later reads them, travels back in time, and gives them to Shakespeare, perpetuating the cycle. In this loop, the works exist without ever being truly created, posing the question, who is the original author? This paradox challenges our notions of authorship, creativity, and the flow of information, suggesting that time travel could lead to scenarios where objects or knowledge exist without a discernible origin. Such situations provoke deeper philosophical inquiries about the nature of existence and the fabric of reality itself. Time travel, while a staple of science fiction, presents profound challenges to our understanding of time, causality, and the universe. Paradoxes like the grandfather and bootstrap paradoxes highlight the intricate and often perplexing implications of altering the temporal continuum. As we continue to explore these concepts, both in theoretical physics and philosophical discourse, we are reminded of the delicate balance that underpins the reality we experience and the potential consequences of tampering with the threads of time. Consider the ticking of a clock, each second slipping away, marking the relentless march of time. Yet, when we delve into the fundamental nature of time, we encounter paradoxes that challenge this intuitive flow. Philosopher J.M.E. McTaggart, in his early 20th century work, argued that our perception of time involves a contradiction, suggesting that time itself might be an illusion. McTaggart introduced two perspectives to analyze time. The A-series. This perspective views events as moving from future to present to past, capturing our everyday experience of time's passage. The B-series. Here, events are ordered based on a fixed relation of earlier than or later than, without any flow from future to past. McTaggart argued that while the A-series is essential for expressing change, it leads to contradictions, implying that our perception of time's passage might be incoherent. He suggested that if time involves both the A-series and the B-series, it leads to a contradiction, and thus, time is unreal. This paradox challenges our conventional understanding of cause and effect, suggesting that altering past events could lead to self-contradictory outcomes. While some theories propose that such paradoxes could be resolved through mechanisms like parallel universes or self-consistency principles, no definitive solutions have been universally accepted. Further complicating our understanding, physicist Stephen Wolfram proposes that our experience of time arises from the interplay between our computational limitations as observers and the computational irreducibility of underlying processes. This perspective suggests that time emerges from more fundamental, timeless rules, challenging our conventional notions of temporal flow. Wolfram's view posits that if we were not computationally bounded, we could perceive the entire future instantly, eliminating the need for a concept of time. Conversely, if there weren't underlying processes with computational irreducibility, there would be no progressive unfolding of events, and thus no experience of time passing. This interplay gives rise to the flow of time that we perceive. Moreover, Wolfram suggests that the directionality of time, often associated with the second law of thermodynamics, emerges from this interplay. The increase in entropy or disorder aligns with our perception of time moving forward, reinforcing the concept of a flowing time. The nature of time remains one of the most profound and perplexing mysteries in both philosophy and physics. Paradoxes like McTaggart's and Wolfram's insights invite us to reconsider our intuitive understanding of time, suggesting that it may not be a fundamental aspect of reality, but rather an emergent phenomenon rooted in deeper, timeless processes. As we continue to explore these concepts, we edge closer to unraveling the true essence of time and its role in the fabric of the universe. Imagine a universe where the fundamental constants, such as the gravitational constant, the electron charge, and the cosmological constant, are even minutely altered. Such changes would render the existence of life, as we know it, impossible. This observation has led to the concept of the fine-tuned universe, suggesting that the cosmos is precisely calibrated to support life. This apparent precision presents a paradox. Is this fine-tuning a product of chance, necessity, or design? Understanding fine-tuning. Fine-tuning refers to the precise values of certain physical constants that allow for the existence of life. Small deviations from these values could lead to a universe inhospitable to life. For example, if the strong nuclear force were slightly weaker, stars like our Sun could not exist, and if it were slightly stronger, stars would burn out too quickly. The term fine-tuning characterizes the sensitive dependence of life-permitting conditions on the values of these fundamental parameters. The anthropic principle. To address the fine-tuning paradox, some scientists and philosophers invoke the anthropic principle, which posits that the universe must have the properties it does because life exists to observe it. This principle suggests that our universe's life-supporting characteristics are not surprising, given that we are here to notice them. However, this explanation has been critiqued for potentially being tautological and not offering a deeper understanding of why the universe is life-permitting. Multiverse hypothesis. An alternative explanation is the multiverse hypothesis, which proposes that our universe is just one of many, each with different physical constants. In such a scenario, it's not unexpected that at least one universe would have the right conditions for life. However, the multiverse theory currently lacks empirical evidence and remains a topic of debate among scientists. Debates and criticisms. The fine-tuning argument has faced several criticisms. Perception of fine-tuning. Some scholars argue that what appears as fine-tuning might be an illusion due to our limited understanding of fundamental physics. They suggest that as our knowledge advances, the seeming fine-tuning may be explained by deeper, more fundamental theories. Carbon chauvinism, assuming that life must be carbon-based and that the conditions we observe are the only ones capable of supporting life, has been termed carbon chauvinism. This perspective may limit our imagination regarding the possible forms that life could take under different conditions. Inverse gambler's fallacy. Some critics argue that invoking the multiverse to explain fine-tuning is akin to the inverse gambler's fallacy, suggesting that it's a flawed application of probabilistic reasoning. The fine-tuning paradox invites profound questions about the nature of our universe and our place within it. While various hypotheses attempt to explain this precise calibration, the lack of empirical evidence for many of these theories leaves the paradox unresolved. As our understanding of physics and cosmology deepens, we may uncover new insights that shed light on whether the universe's life-supporting properties are the result of chance, necessity, or design. Imagine a universe where the expansion of space itself is accelerating, pushing galaxies away from each other at an ever-increasing pace. This phenomenon, attributed to a mysterious force known as dark energy, challenges our fundamental understanding of physics and cosmology. The dark energy paradox lies in its elusive nature. While we observe its effects, its true identity and origin remain unknown, prompting profound questions about the fate of the universe. Understanding dark energy. Dark energy is a hypothetical form of energy that permeates all of space, driving the accelerated expansion of the universe. Its existence is inferred from astronomical observations, particularly the redshift of distant galaxies and the cosmic microwave background radiation. However, despite its significant impact on cosmic dynamics, dark energy has never been directly observed or measured, leading to various theories about its nature and behavior. Recent observations and anomalies. Recent studies have revealed intriguing anomalies that challenge our current understanding of dark energy. Hubble tension. Measurements of the Hubble constant, which describes the rate of the universe's expansion, have yielded conflicting results. The James Webb Space Telescope confirmed that the universe is expanding at a rate about 8% faster than previously expected, suggesting discrepancies that could point to unknown aspects of dark energy or gravity. Dynamic dark energy. Research from the Dark Energy Spectroscopic Instrument, DESI, indicates that dark energy may not be a constant force as traditionally assumed. Instead, it might vary over time, challenging existing cosmological models and our understanding of cosmic acceleration. Alternative explanations. Some scientists propose that the effects attributed to dark energy might result from observational artifacts or alternative cosmological models. For instance, timescape cosmology suggests that our measurements of cosmic expansion could be influenced by the way we calculate time and space, implying that dark energy might be an illusion. However, such theories face significant scrutiny and have not gained widespread acceptance. Theoretical perspectives. The nature of dark energy remains one of the most profound mysteries in cosmology. Some theories propose that it could be related to the energy inherent in the vacuum of space, while others suggest it might be a manifestation of modifications to general relativity at cosmological scales. Understanding dark energy is crucial, as it influences the ultimate fate of the universe, potentially leading to scenarios like the Big Rip, where the expansion continues to accelerate until galaxies, stars, and even atoms are torn apart. The dark energy paradox underscores the limits of our current knowledge and the need for new physics to explain the universe's accelerating expansion. As observational techniques advance and theoretical models evolve, scientists strive to uncover the true nature of dark energy, aiming to resolve these cosmic enigmas and deepen our understanding of the universe's past, present, and future. Imagine a realm where the very fabric of space-time is woven from quantum threads, where gravity bends and twists at the smallest scales, and where the laws of physics as we know them break down. This is the frontier of the quantum gravity conundrum, a quest to reconcile the smooth, continuous nature of gravity described by general relativity with the discrete, probabilistic world of quantum mechanics. Solving this conundrum is one of the most profound challenges in modern physics, promising to unveil the deepest secrets of the universe. The essence of the quantum gravity problem. At the heart of the quantum gravity conundrum lies a fundamental incompatibility. General relativity, this theory, formulated by Albert Einstein, describes gravity as the curvature of space-time caused by mass and energy. It operates seamlessly at macroscopic scales, governing the motion of planets and the dynamics of galaxies. Quantum mechanics. This framework governs the behavior of particles at the smallest scales, where phenomena like superposition and entanglement prevail. It treats forces, including gravity, as quantized interactions mediated by particles. Attempting to merge these two theories leads to mathematical inconsistencies and conceptual paradoxes, particularly in extreme environments like black holes or the moments following the Big Bang. Understanding how gravity operates at these scales is crucial for developing a unified theory. Recent theoretical approaches. Researchers are exploring various avenues to bridge the gap between quantum mechanics and gravity. Extra dimensions and fuzzy gravity, introducing additional spatial dimensions, has been proposed as a means to unify gravity with quantum mechanics. A study suggests that adding extra dimensions to a theory known as fuzzy gravity may help bridge the gap between quantum mechanics and relativity. Emergent gravity. This perspective posits that gravity is not a fundamental interaction, but emerges from a collective behavior of microscopic degrees of freedom. It suggests that space-time and gravitational effects arise from more fundamental, non-gravitational physics. Holographic principles and black hole physics. Exploring the quantum mechanics of black holes has provided insights into the nature of space-time and gravity. Studies indicate that different descriptions of quantum gravity, such as the Euclidean gravitational path integral and holographic quantum systems, are physically equivalent, offering new perspectives on how gravity operates at the quantum level. Philosophical and conceptual considerations. Some physicists propose rethinking the very nature of gravity in the context of quantum theory. Jonathan Oppenheim suggests that gravity might remain classical, interacting with the quantum world through stochastic mechanisms, thereby avoiding the need for a full quantum theory of gravity. The quantum gravity conundrum represents a profound frontier in our quest to understand the universe. While significant progress has been made through innovative theories and experimental observations, a complete and consistent theory of quantum gravity remains elusive. Continued exploration at the intersection of quantum mechanics and general relativity is essential, as it holds the promise of unlocking the deepest mysteries of the cosmos and revealing the true nature of reality itself. In the microscopic realm of quantum mechanics, particles such as electrons do not have definite positions or velocities until observed. Instead, they are described by wave functions, mathematical constructs that encapsulate all possible states of a system. The nature of these wave functions has sparked intense debate among physicists. Do they represent real, physical entities, or are they merely abstract tools for predicting measurement outcomes? This question lies at the heart of understanding the fundamental principles governing our universe. Understanding the wave function. In quantum mechanics, the wave function, denoted as psi, is a complex-valued function that provides a complete description of a quantum system. The square of its absolute value, psi superscript 2, gives the probability density of finding a particle in a particular region of space at a given time. This probabilistic interpretation was introduced by Max Born in 1926, marking a departure from classical deterministic views. For systems with multiple particles, the wave function becomes a function of all particle positions and spins, reflecting the system's overall quantum state. The symmetry properties of the wave function, especially concerning identical particles, are crucial in determining the statistical behavior of particles, leading to the distinction between bosons and fermions. Interpretations of the wave function. The wave function's role has led to various interpretations regarding its physical reality. Copenhagen interpretation proposes that the wave function represents our knowledge of a system rather than the system's physical state itself. Upon measurement, the wave function collapses to a specific state, reflecting the transition from a superposition of possibilities to a single reality. Many worlds interpretation suggests that all possible outcomes of quantum measurements actually occur, each in its own separate universe. Here, the wave function never collapses. Instead, it continually evolves, encompassing all realities. Pilot wave theory, Boltzmann mechanics, introduces hidden variables to restore determinism, asserting that particles have definite positions and velocities guided by a pilot wave. The wave function in this view is a real, physical field influencing particle dynamics. Objective collapse theories propose that wave function collapse is a real, physical process triggered by certain conditions, such as gravity or complexity, suggesting that the wave function represents a physical entity that undergoes spontaneous reduction to a definite state. Quantum Bayesianism, QBism, interprets the wave function as a subjective state of knowledge or belief about a system, emphasizing the role of the observer in assigning probabilities to different outcomes. Philosophical and conceptual considerations. The debate over the wave function's reality raises profound philosophical questions about the nature of reality and observation. Measurement problem. How does the act of measurement cause the wave function to collapse, and what determines the outcome? Reality of the quantum world. Do quantum entities exist in definite states independent of observation, or is reality fundamentally probabilistic and observer-dependent? Determinism versus indeterminism. If the wave function represents all possible outcomes, does this imply a deterministic universe, or is indeterminacy intrinsic to nature? Nonlocality and entanglement. How does the instantaneous action at a distance observed in entangled particles reconcile with the principles of locality and causality? Implications for quantum computing and technology. Understanding the nature of the wave function has practical implications for emerging technologies. Quantum computing utilizes principles like superposition and entanglement, which are directly related to the behavior of wave functions, to perform computations beyond the capabilities of classical computers. Quantum cryptography relies on the principles of quantum mechanics, including the behavior of wave functions, to create secure communication channels that are theoretically immune to eavesdropping. The nature of the wave function remains one of the most intriguing and debated aspects of quantum mechanics. While it serves as a powerful tool for predicting experimental outcomes, its interpretation challenges our deepest intuitions about reality. As research advances and new experiments shed light on these quantum mysteries, our understanding of the wave function's true nature may eventually lead to a more complete and coherent picture of the universe at its most fundamental level. In our everyday experience, time flows in one direction, from past to present to future. This progression aligns with the second law of thermodynamics, which states that entropy, a measure of disorder, tends to increase over time. However, this natural inclination toward disorder presents a conundrum when we consider the universe's inception, the Big Bang. The universe began in an extraordinarily low entropy state, yet fundamental physical laws are time-symmetric, meaning they don't inherently distinguish between past and future. This disparity between the time-symmetric nature of physical laws and the observed arrow of time leads to the low-entropy past paradox. The second law of thermodynamics and entropy. The second law of thermodynamics dictates that in an isolated system, entropy does not decrease. It either increases or remains constant. This principle introduces a directionality to time, known as the arrow of time, where processes evolve from past to future in a manner that aligns with increasing entropy. However, if we trace this arrow backward, we encounter a universe that was once in a highly ordered, low-entropy state, the Big Bang. This observation raises the question: how can time-symmetric laws lead to an irreversible progression toward higher entropy? Sorites Paradox. Time reversibility versus irreversibility. Sorites Paradox highlights the tension between the time-symmetric nature of fundamental physical laws and the macroscopic irreversibility we observe. It suggests that if the fundamental laws are time-symmetric, then any process that occurs should also have a time-reverse counterpart that is equally probable. This symmetry implies that the increase in entropy we observe should be just as likely to reverse, leading to a decrease in entropy, a notion that contradicts our experience of time's unidirectional flow. Addressing the paradox, the past hypothesis. To reconcile this discrepancy, physicists propose the past hypothesis, which posits that the universe began in a low-entropy state. This hypothesis serves as a boundary condition that explains the observed directionality of time. By starting with a low-entropy initial condition, the universe's evolution naturally progresses toward higher entropy, aligning with the second law of thermodynamics and the observed arrow of time. However, this hypothesis raises further questions about the origin of the low-entropy state and its implications for our understanding of time's nature. Philosophical and theoretical considerations. The low-entropy past paradox delves into deep philosophical and theoretical realms. Origin of the low-entropy state. What mechanisms led to the universe's initial low-entropy condition? And why is it not just a statistical fluctuation among possible states? Time's arrow and cosmology. How does the concept of a low-entropy past influence our understanding of cosmological events and the universe's ultimate fate? Time symmetry versus asymmetry. How can we reconcile the time-symmetric laws governing microscopic interactions with the macroscopic asymmetry we observe in time's flow? The low-entropy past paradox underscores the complexities inherent in our understanding of time, entropy, and the universe's origins. While the past hypothesis offers a plausible explanation for the observed arrow of time, it also invites deeper inquiry into the fundamental laws governing our cosmos. As research advances, unraveling these mysteries may provide profound insights into the nature of time and the universe itself. Consciousness encompasses our thoughts, emotions, and perceptions, the very essence of our subjective experience. Philosopher David Chalmers introduced the hard problem of consciousness, highlighting the challenge of explaining how physical processes in the brain give rise to the rich tapestry of subjective experience. Understanding the hard problem. While neuroscience has made significant strides in mapping brain activity to cognitive functions, it has yet to elucidate how these physical processes translate into conscious experience. This gap between measurable brain activity and the qualitative nature of experience is the crux of the hard problem. Philosophical perspectives. Various philosophical approaches attempt to address this conundrum. Type A materialism, eliminative materialism/illusionism. This viewpoint suggests that our intuitive understanding of consciousness is flawed and that conscious experience is an illusion. Philosophers like Daniel Dennett and Keith Frankish advocate for this perspective, proposing that what we perceive as consciousness does not exist in the way we think. Type E dualism, proposing that consciousness and physical processes are distinct. This perspective suggests that the mind operates independently of the brain, presenting challenges to materialistic explanations. New Mysterianism. Philosopher Colin McGinn posits that human cognitive limitations prevent us from comprehending the relationship between consciousness and physical processes, suggesting that this mystery may be beyond our intellectual reach. The easy problems versus the hard problem. Cognitive scientist Daniel Dennett differentiates between the easy problems of consciousness, such as understanding brain functions and behaviors, and the hard problem, which delves into why and how these processes are accompanied by subjective experience. He argues that solving the easy problems may eventually shed light on the hard problem. Recent discussions and ethical implications. Advancements in artificial intelligence have sparked debates about machine consciousness. If AI systems were to exhibit behaviors akin to conscious beings, questions about their rights and ethical treatment would emerge, challenging our definitions of consciousness and personhood. The hard problem of consciousness remains one of the most profound challenges in science and philosophy. While various theories offer insights, a comprehensive understanding of how subjective experience arises from physical processes continues to elude us. This enigma not only deepens our understanding of the mind, but also influences ethical considerations in technology and artificial intelligence. The Ship of Theseus Paradox is a thought experiment that delves into questions of identity and change. It challenges our understanding of whether an object remains fundamentally the same when all its components are replaced over time. Originating from ancient Greek philosophy, this paradox continues to intrigue scholars and thinkers. The thought experiment. Imagine a ship owned by Theseus, the mythical king of Athens. Over time, as each part of the ship decays, it is replaced with a new, identical component. This process continues until every single part of the ship has been replaced. The central question arises, is this still the original ship of Theseus, or has it become a new entity? Historical context. The earliest mention of this paradox comes from Plutarch, who used it to explore the nature of identity and persistence. He described how the Athenians maintained Theseus's ship by replacing decayed planks with new timber, raising the question of whether the ship remained the same after all parts were replaced. Centuries later, philosopher Thomas Hobbes extended the thought experiment by introducing a scenario where the removed wooden parts were gathered and reassembled into a new ship. This led to further contemplation about which, if either, of the ships could be considered the original. Philosophical implications. The Ship of Theseus Paradox raises several philosophical questions. Material constitution versus identity. Does an object's identity depend on the material it is made of, or is it defined by its form and function? Continuity and change. How do we reconcile the continuous identity of an object amidst constant change and replacement of its parts? Temporal persistence. At what point, if any, does an object cease to be itself due to cumulative changes over time? Proposed resolutions. Philosophers have proposed various solutions to address the paradox. Constitution is not identity. This perspective suggests that the material out of which an object is made is distinct from the object itself. Therefore, replacing all parts does not change the object's identity. Temporal parts theory, proposed by philosopher David Lewis. This theory posits that objects are extended in time and consist of temporal parts. Each time slice of the object is a distinct part, and the object's identity is a series of these temporal parts. Cognitive science perspective. Some scholars argue that the paradox arises from human cognitive biases, suggesting that our intuitions about object identity may not align with the complexities of the physical world. This view posits that the confusion stems from our mental constructs rather than the nature of the object itself. Deflationism. This view holds that debates about the identity of objects like the Ship of Theseus are merely verbal disputes, stemming from different uses of the term identity, rather than substantive disagreements. Gradual replacement view. This perspective suggests that as long as the replacement of parts occurs gradually, maintaining functional continuity, the object retains its identity. However, if all parts are replaced simultaneously, it would be considered a new object. Bundle theory. This theory proposes that objects are merely collections, bundles, of their properties. If all properties, parts, change, the object is no longer the same. No change view. Some argue that as long as the form and function of the object remain consistent, it retains its identity, regardless of the replacement of individual parts. Real-world applications and analogies. The ship of Theseus paradox has practical applications in various fields. Personal identity. It parallels questions about human identity, such as whether a person remains the same despite physical and psychological changes over time. Artificial intelligence. In the realm of AI, if a machine's components are gradually replaced or upgraded, does it remain the same entity? Organizational identity. Businesses and institutions often undergo changes in personnel and structure. The paradox prompts questions about their continued identity. The ship of Theseus paradox remains a compelling exploration of how we perceive identity and change. It challenges our intuitions and encourages deeper reflection on the nature of objects and their persistence over time. While various philosophical perspectives offer differing resolutions, the paradox continues to stimulate discussion and inquiry into the fundamental aspects of existence and identity. The liar paradox is a classic conundrum in philosophy and logic that challenges our understanding of truth and reference. It arises from statements that refer to themselves in a contradictory manner, leading to logical dilemmas that have intrigued scholars for centuries. Origin and classical formulation. The paradox traces its roots to ancient Greece, attributed to Epimenides, a Cretan philosopher who purportedly stated, "All Cretans are liars." If Epimenides, himself a Cretan, is truthful, then his declaration implies that all Cretans lie, including himself, which leads to a contradiction. A more direct example is the statement, "This sentence is false." If the sentence is true, then it must be false as it claims, but if it's false, then it must be true, creating an endless loop of contradiction. The liar paradox has significantly influenced the development of formal logic and the philosophy of language. Kurt Gödel's first incompleteness theorem, for instance, employs a liar-like sentence to demonstrate that within any sufficiently powerful axiomatic system, there exist true statements that are unprovable within the system. This result underscores inherent limitations in formal mathematical systems and highlights the complexities introduced by self-referential statements. Additionally, the paradox has inspired alternative logical frameworks, such as para-consistent logics, which tolerate contradictions without leading to logical explosion, thereby offering a more nuanced approach to reasoning in the presence of paradoxical statements. These developments illustrate the profound impact of the liar paradox on both theoretical and applied aspects of logic and computation. Philosophical and logical implications. The liar paradox exposes limitations in classical two-valued logic, where statements are either true or false. It suggests that self-referential statements can defy such binary classifications, prompting the need for more nuanced logical frameworks. This paradox has influenced various fields, including mathematics and computer science, highlighting the complexities of self-reference and truth. Modern approaches and resolutions. To address the paradox, scholars have developed alternative logical systems. Hierarchical solutions. These involve organizing statements into levels, where a statement about truth belongs to a higher level than the statements it describes, thereby avoiding self-reference. Para-consistent logics. These allow for contradictions to exist without collapsing the entire logical system, accommodating statements that can be both true and false. Dialetheism. This approach accepts that some statements are both true and false, embracing the paradox as a legitimate aspect of reality. Real-world applications and analogies. The liar paradox extends beyond theoretical discourse, influencing practical domains. Computer science. In programming, self-referential code can lead to infinite loops or undefined behaviors, mirroring the paradox's implications. Artificial intelligence. Developing AI that can navigate self-referential statements requires sophisticated logic to prevent contradictions and ensure reliable reasoning. Linguistics. Understanding how languages handle self-reference aids in parsing and interpreting complex sentence structures. Embracing the complexity of truth. The liar paradox remains a profound testament to the complexities inherent in language, logic, and truth. It challenges our foundational assumptions and encourages the exploration of more sophisticated systems to accommodate the nuances of self-reference and contradiction. By acknowledging and studying such paradoxes, we deepen our comprehension of logical frameworks and the intricate nature of human reasoning. Russell's paradox, discovered by British philosopher and logician Bertrand Russell in 1901, exposed a fundamental contradiction within naive set theory. This paradox questioned the very foundation of mathematics and logic, prompting a re-evaluation of set theoretic principles. The paradox explained, consider the set of all sets that do not contain themselves as a member. If such a set exists, denoted as R, then, if R is a member of itself, it contradicts its definition, as it should not contain itself. If R is not a member of itself, it aligns with its definition, as it should contain itself. This cyclical reasoning leads to a logical contradiction, highlighting a flaw in the unrestricted comprehension axiom of naive set theory. Historical context and impact. Prior to this discovery, set theory was considered a solid foundation for all of mathematics. George Cantor's development of set theory in the late 19th century introduced concepts such as cardinality and the distinction between countable and uncountable sets. Cantor's work was initially met with resistance due to its counterintuitive nature, but it eventually became a cornerstone of modern mathematics. Russell's paradox revealed that allowing any definable collection to form a set led to inconsistencies, challenging the perceived reliability of set theory. This realization prompted a foundational crisis in mathematics, as the very basis of mathematical logic was called into question. Responses and resolutions. In reaction to the paradox, mathematicians developed axiomatic set theories to avoid such contradictions. Zermelo-Fraenkel's set theory introduced axioms like the axiom of separation, limiting set formation to subsets of existing sets, thereby preventing the construction of problematic sets like R. Type theory, proposed by Russell himself. This approach organizes objects into hierarchies, ensuring that sets can only contain sets from lower levels, thus avoiding self-referential definitions. Von Neumann-Bernay's Gödel set theory, an extension of Zermelo-Fraenkel set theory, NBG incorporates classes as collections of sets, providing a more robust framework to handle the paradox. New foundations, developed by Willard Van Orman Quine. NF is an alternative set theory that attempts to resolve the paradox by restricting the comprehension axiom. Philosophical implications. Beyond mathematics, the paradox influenced philosophical discussions on self-reference and logical systems, prompting a re-evaluation of how language and logic can lead to contradictions. It also spurred debates on the nature of mathematical objects and the foundations of mathematical truth. Bertrand Russell, A Brief Biography. Born on May 18, 1872, in Trelech, Monmouthshire, Wales, Bertrand Russell was a prominent British philosopher, logician, and social reformer. He was a leading figure in the analytic movement in Anglo-American philosophy and was awarded the Nobel Prize for Literature in 1950. Russell's contributions to logic, epistemology, and the philosophy of mathematics have had a lasting impact on 20th century thought. Russell's paradox serves as a critical reminder of the complexities inherent in foundational logical systems. It underscores the necessity for rigorous axiomatic frameworks to ensure consistency in mathematical and logical reasoning. The ongoing exploration of such paradoxes continues to shape our understanding of logic, mathematics, and philosophy. The unexpected hanging paradox, also known as the surprise execution paradox, presents a compelling scenario that challenges our understanding of expectation and knowledge. It involves a condemned prisoner, a judge's cryptic proclamation, and a week filled with logical twists. Dissecting the paradox. The scenario. A judge informs a prisoner that he will be hanged at noon on one weekday in the upcoming week, Monday to Friday. The twist. The execution will be a surprise. The prisoner will not know the day of the hanging until the executioner arrives at his cell at noon that day. The prisoner's reasoning. The prisoner, attempting to deduce the day of his execution, reasons as follows. Eliminating Friday. If he hasn't been hanged by Thursday noon, the hanging must occur on Friday. But this contradicts the surprise element, as he'd anticipated. Therefore, the hanging cannot be on Friday. Eliminating Thursday. With Friday ruled out, if he's not hanged by Wednesday noon, the hanging must be on Thursday. But again, he'd expect it, violating the surprise condition. Thus, Thursday is also eliminated. Continuing the elimination, applying the same logic, he concludes that the hanging cannot occur on Wednesday, Tuesday, or Monday. The unexpected twist. Despite his reasoning, the prisoner is surprised when the executioner arrives on Wednesday of the week. This outcome defies his logical deductions and highlights the paradox's challenge to our understanding of knowledge and expectation. Logical and philosophical implications. The paradox delves into concepts of self-reference, knowledge, and expectation. It questions how individuals process information about future events and the limits of logical reasoning when dealing with uncertain outcomes. Variations and discussions. The unexpected hanging paradox has inspired numerous discussions and variations, exploring its implications in different contexts. For instance, the paradox has been analyzed in the context of Moore's paradox, which deals with statements that are paradoxical when one believes them, but does not believe them. The unexpected hanging paradox not only challenges our intuitive understanding of surprise and expectation, but also serves as a gateway to exploring deeper philosophical questions about determinism, free will, and the nature of knowledge. It invites contemplation on how individuals reconcile logical reasoning with unpredictable outcomes, highlighting the complexities inherent in human cognition and the limits of formal logic when applied to real-world scenarios. This paradox underscores the intricate interplay between expectation and reality, prompting ongoing discussions in both philosophical and psychological domains about the mechanisms that govern human thought and anticipation. Embracing the paradox. The unexpected hanging paradox serves as a fascinating exploration into the complexities of human reasoning and expectation. It challenges our intuitive understanding of knowledge and surprise, prompting deeper reflection on how we anticipate and process future events. The Sorites Paradox, also known as the paradox of the heap, delves into the complexities arising from vague predicates, terms without clear-cut boundaries. Originating from ancient philosophical discourse, this paradox challenges our understanding of concepts that lack precise definitions. Deconstructing the paradox. Understanding the Sorites Paradox. The term Sorites is derived from the Greek word for heap. The paradox typically unfolds through a scenario involving a heap of sand. Starting point: begin with a heap of sand consisting of, say, 1 million grains. Gradual reduction. Remove grains one at a time. The question: at what point does the collection cease to be considered a heap? Intuitively, removing a single grain doesn't seem to change the status of being a heap. However, after successive removals, we face the question, at what exact number does it stop being a heap? This dilemma exposes the challenges in applying vague terms to real-world situations. Real-world examples of vagueness. Beyond heaps of sand, vagueness permeates everyday language and concepts. Baldness. At what point does a person transition from being not bald to bald? Tallness. How tall must one be to be considered tall? Aging. When does someone become old? These examples underscore the absence of clear-cut boundaries in many classifications we routinely make. Philosophical and logical implications. The Sorites Paradox invites deep philosophical inquiry into the nature of concepts and language. Continuum problem. It highlights the difficulty in drawing precise lines within continuous spectra. Epistemic uncertainty. The paradox challenges our knowledge about when and how vague predicates apply. Logical frameworks. Traditional binary logic struggles with the gray areas presented by vague terms, prompting the exploration of alternative logical systems. Proposed resolutions. Various approaches have been proposed to address the challenges posed by the Sorites paradox. Fixed boundary approach. Establishing a specific threshold, e.g., a heap requires at least 100 grains to delineate when a term applies. However, this method is often criticized for its arbitrariness. Epistemicism, suggesting that there are precise boundaries, but they are unknowable, thus embracing the inherent vagueness without attempting to eliminate it. Multi-valued logic, introducing systems where truth values are not limited to true or false, but include degrees of truth to better capture the nuances of vague predicates. Group consensus, determining the application of vague terms based on collective agreement or societal usage, acknowledging that meanings can be fluid and context-dependent. Practical applications and implications. The Sorites paradox extends beyond theoretical discussions, influencing various practical domains. In economics, for instance, it challenges the analysis of consumer preferences, especially when individuals exhibit indifference between quantities that differ minutely. This scenario complicates the establishment of precise thresholds for decision-making and policy formulation. Similarly, in legal and ethical debates, such as those surrounding abortion, the paradox highlights difficulties in defining exact points where moral or legal statuses change, given the continuum of development. These real-world applications underscore the pervasive nature of the Sorites paradox, prompting ongoing discussions about how to handle concepts that resist clear-cut definitions. The Sorites paradox serves as a poignant reminder of the complexities inherent in human language and cognition. It challenges us to confront the limitations of our conceptual frameworks and encourages the development of more nuanced approaches to understanding and communicating about the world around us. Newcomb's paradox presents a thought-provoking scenario that challenges our understanding of decision-making, prediction, and free will. It juxtaposes two principles of game theory, expected utility and strategic dominance, leading to conflicting recommendations about the optimal choice. Dissecting the paradox. The scenario. Imagine a game where you are presented with two boxes. Box A contains $1,000. Box B contains either $1 million or nothing, depending on a prediction. Before you make your choice, a highly accurate predictor forecasts your decision. If the predictor anticipates you will select both boxes, box B is left empty. If the predictor foresees you choosing only box B, is filled with $1 million. You have the option to choose both boxes, A and be guaranteed $1,000 from box A. Select only box B. Potentially receive $1 million if the predictor was correct. The decision dilemma. Expected utility principle. Considering the predictor's high accuracy, choosing only box B seems optimal, as it maximizes expected gains. Dominance principle. Selecting both boxes guarantees an additional $1,000 regardless of the predictor's accuracy, suggesting it's the better choice. This dichotomy illustrates the tension between maximizing expected utility and adhering to dominant strategies. Philosophical and theoretical implications. Newcomb's paradox delves into profound questions about causality, free will, and determinism. Causality and prediction. If a predictor can foresee choices with near certainty, does this imply determinism, challenging notions of free will? Free will versus predestination. The scenario prompts debate on whether our choices are genuinely free or influenced by predictive knowledge. Ethical considerations. The paradox parallels real-life dilemmas where predictive technologies influence decisions, raising concerns about autonomy and manipulation. Real-world analogies. This thought experiment mirrors situations where predictive analytics impact personal choices. Marketing and consumer behavior. Companies anticipate purchasing habits to tailor advertisements, influencing consumer decisions. Criminal justice. Risk assessment tools predict recidivism, affecting sentencing and parole decisions, sparking debates about fairness and bias. Practical applications and implications. Newcomb's paradox extends beyond theoretical musings, offering insights into real-world scenarios where prediction and decision-making intersect. In economics, for instance, understanding consumer behavior involves anticipating choices based on past actions, akin to the predictor's role. Marketers often rely on data analytics to forecast purchasing decisions, tailoring strategies to influence consumer behavior effectively. Similarly, in criminal justice, risk assessment tools predict recidivism by analyzing offenders' histories, guiding parole decisions. However, these predictions raise ethical concerns about determinism and free will, mirroring debates sparked by Newcomb's paradox. Recognizing the implications of predictive models challenges us to balance statistical insights with respect for individual autonomy, ensuring that predictions inform without constraining personal freedom. Navigating the paradox. Newcomb's paradox serves as a compelling exploration of the complexities at the intersection of prediction, decision-making, and free will. It challenges our intuitions and invites deeper reflection on the nature of choice and autonomy in a world increasingly influenced by predictive technologies. The dilemma of unrestricted tolerance. The paradox of tolerance, introduced by philosopher Karl Popper in his 1945 work The Open Society and Its Enemies, presents a compelling challenge to the concept of unlimited societal tolerance. Popper argued that a truly tolerant society must retain the right to deny tolerance to those who promote intolerance. He posited that if intolerant ideologies are allowed unchecked expression, they could exploit open society values to erode or destroy tolerance itself through authoritarian or oppressive practices. Exploring the paradox. Understanding the paradox. Popper's central thesis posits that if a tolerant society permits the existence and propagation of intolerant ideologies, these ideologies could exploit the freedoms provided to them, ultimately eroding the principles of tolerance and democracy. This scenario presents a dilemma. Should a tolerant society tolerate intolerance, or does doing so risk its own demise? Practical implications. In real-world contexts, this paradox influences debates on freedom of speech and the limits of acceptable discourse. For instance, should platforms and societies allow hate speech under the guise of free expression, knowing that such speech can incite violence and suppress the freedoms of others? This question underscores the tension between maintaining an open society and protecting it from forces that seek to dismantle its foundational values. Balancing tolerance and protection. Addressing the paradox requires a nuanced approach that balances the virtues of tolerance with the necessity of protecting societal values. Philosophers like John Rawls have suggested that while a just society should generally tolerate diverse viewpoints, there must be limits when expressions of intolerance pose a tangible threat to liberty and public order. This perspective advocates for a protective stance against ideologies that aim to suppress the freedoms of others. Defining boundaries. Establishing clear boundaries between acceptable and intolerant behaviors is crucial. This involves discerning between protecting free speech and preventing harm caused by speech that incites violence or discrimination. Determining these limits is complex and often subjective, requiring continuous societal dialogue and legal considerations to navigate the delicate balance between freedom and protection. Historical context and relevance. The paradox of tolerance gained prominence in the 20th century, particularly in the context of rising authoritarian regimes. Popper introduced the concept to explain how a society's tolerance of intolerance could lead to its own destruction. This insight remains relevant today, as societies grapple with the challenges of maintaining democratic values in the face of extremist ideologies. Upholding democratic values. The paradox of tolerance challenges societies to reflect on the complexities inherent in maintaining a free and just community. It emphasizes the importance of setting boundaries to prevent the erosion of the very freedoms that define a tolerant society. By critically engaging with this paradox, societies can strive to uphold democratic values while safeguarding against the rise of intolerance. The Abilene Paradox, introduced by management expert Jerry B. Harvey in 1974, describes a phenomenon where a group collectively decides on a course of action that contradicts the preferences of its individual members. This occurs because each member assumes their own dissenting opinion is unique, leading them to conform to what they believe others desire, thereby fostering a false consensus. Dissecting the paradox. The paradox in action. Harvey illustrates the Abilene Paradox with a common family scenario. A family is sitting in the living room on a hot Texas afternoon. After a period of silence, the father says, "Let's go to Abilene for dinner." The mother replies, "I don't want to go to Abilene, but if the rest of you do, I'll go." The daughter chimes in, "I don't want to go to Abilene either, but if Mom and Dad want to, I'll go." They all drive 53 miles to Abilene, where they have a mediocre meal and return home. Later, they discover that each of them was reluctant to go, but assumed the others were eager, leading to a collective decision that no one wanted. Psychological underpinnings. The Abilene Paradox is rooted in a failure to manage agreement within groups. Individuals often suppress their true preferences, fearing conflict or believing their dissenting opinions are isolated. This lack of open communication leads to decisions that do not reflect the group's actual desires. Organizational implications. In organizational settings, the Abilene Paradox can result in misguided strategies and initiatives. When team members do not voice their concerns or preferences, decisions may be made that are misaligned with the group's objectives, leading to inefficiencies and dissatisfaction. Real-world example. A study at Makerere University Business School in Uganda examined the Abilene Paradox in decision-making. Faculty members voted to support a legal action against the Ministry of Education, assuming others strongly supported the idea. However, interviews revealed that many did not consider it a viable solution but thought others strongly supported it, highlighting the paradox's impact. Mitigating the paradox. Fostering open communication. Encouraging an environment where team members feel safe to express their true opinions can prevent the emergence of false consensus. Clarifying assumptions. Regularly discussing and validating assumptions within the group can ensure that decisions are based on accurate perceptions of collective preferences. Establishing decision-making protocols. Implementing structured decision-making processes, such as anonymous voting or feedback mechanisms, can help surface individual preferences that might otherwise be suppressed. Leadership awareness. Leaders should be vigilant about the dynamics within their teams, actively seeking input from all members and being mindful of the potential for the Abilene paradox to influence decisions. Navigating group dynamics. The Abilene paradox serves as a cautionary tale about the costs of conformity and the silent power of assumed consensus. By recognizing the signs of this paradox and implementing strategies to promote open dialogue and critical thinking, groups can make decisions that truly reflect the collective will, avoiding the pitfall of pursuing paths that no one genuinely desires. The burden of abundance. In contemporary society, individuals are inundated with an unprecedented array of choices, from consumer products to lifestyle options. While this abundance is often hailed as a testament to freedom and prosperity, it paradoxically can lead to decision fatigue, anxiety, and diminished satisfaction. Psychologist Barry Schwartz, in his book The Paradox of Choice, Why More is Less, explores how having too many options can be counterproductive, leading to feelings of regret and paralysis. The psychological impact of choice. The cognitive load of abundance. Schwartz suggests that an overabundance of choices requires more cognitive effort, leading to decision fatigue and increased regret over our selections. This phenomenon occurs because with so many options, it becomes harder to make decisions, and we may feel less satisfied with our choices, wondering if we could have made a better one. Maximizers versus satisficers. The paradox of choice also introduces the concepts of maximizers and satisficers. Maximizers strive to make the best possible choice, often exhausting themselves by seeking out every possible option to ensure optimality. In contrast, satisficers are content with a choice that meets their criteria, accepting good enough. Schwartz argues that satisficing leads to greater happiness, as it reduces the stress associated with exhaustive searching and the potential regret of missed opportunities. Cultural reflections and social implications. Culturally, the paradox of choice reflects a shift from communal decision-making to individualistic choices. In the past, many decisions were made collectively within families or communities, providing a support system that alleviated the burden of choice. Today, individuals face the responsibility of making numerous decisions independently, which can lead to feelings of isolation and overwhelm. Schwartz highlights that this shift may contribute to societal issues such as depression and anxiety. Strategies for coping with choice overload. Setting clear priorities. Define what truly matters to you, which can streamline decision-making and reduce the allure of less important options. Limiting options. Intentionally narrowing down choices can prevent overwhelm and lead to more satisfying decisions. Embracing good enough. Accept that perfection is often unattainable and that making a satisfactory choice is both realistic and healthy. Seeking external input. Consulting with trusted friends, family, or mentors can provide valuable perspectives and ease the decision-making process. Finding freedom within constraints. The paradox of choice challenges the notion that more options inherently lead to greater happiness. Instead, it suggests that an overabundance of choices can be paralyzing and diminish satisfaction. By understanding this paradox and implementing strategies to manage choices, individuals can navigate the complexities of modern life more effectively, finding freedom within the constraints they set for themselves. The enigma of fictional emotions. The paradox of fiction delves into the intriguing question of how individuals can experience genuine emotions, such as joy, sadness, or fear, toward characters and events that they know are entirely fictional. This paradox challenges our understanding of belief, emotion, and imagination, prompting philosophical debates about the nature of our responses to art and storytelling. Unpacking the paradox. The core dilemma. The paradox is often presented through three seemingly plausible premises. To be emotionally moved, we must believe that the entities or events in question truly exist. When engaging with fiction, we do not hold beliefs about the existence of fictional characters or events. Despite this lack of belief, we frequently experience strong emotions in response to fictional narratives. These premises appear logically incompatible, yet each resonates with our everyday experiences, highlighting the complexity of our engagement with fiction. Philosophical perspectives and responses. Over the years, philosophers have proposed various theories to resolve this paradox. Quasi-emotion theory. This perspective suggests that our emotional responses to fiction are not genuine emotions, but are akin to them. They are make-believe emotions, distinct from our reactions to real-life events. Imaginative engagement. Some scholars argue that when we engage with fiction, we enter an imaginative state where our emotional responses are appropriate, even if we don't believe in the existence of fictional entities. Evaluative belief theory. This approach posits that we hold evaluative beliefs about fictional characters and events, such as judgments about their actions or moral standing, which elicit genuine emotional responses without necessitating belief in their existence. Cultural and psychological significance. Understanding our emotional responses to fiction has broader implications. Empathy development. Fiction allows us to experience diverse perspectives and emotions, enhancing our empathy and social understanding. Emotional regulation. Engaging with fictional narratives can serve as a safe outlet for exploring complex emotions, contributing to emotional well-being. Cognitive processing. Interacting with fictional scenarios challenges our cognitive faculties, promoting critical thinking and problem-solving skills. Embracing the complexity of fictional emotions. The paradox of fiction invites us to reflect on the intricate ways we interact with art and storytelling. While the philosophical debate continues, the emotional richness we derive from fiction remains a testament to the depth of human imagination and empathy. The essence of the paradox. The Allais paradox, formulated by French economist Maurice Allais in 1953, presents a scenario that contradicts the predictions of expected utility theory. This theory posits that individuals make decisions by considering the expected outcomes of their choices, aiming to maximize utility. However, the paradox illustrates that people often deviate from this rational model when faced with certain probabilistic choices. Dissecting the paradox. The classic scenario. Participants are presented with two distinct experiments, each offering a choice between two gambles. Experiment 1. Gamble 1A, a 100% chance to win $1 million. Gamble 1B, an 89% chance to win $1 million, a 10% chance to win $5 million, and a 1% chance to win nothing. Experiment 2. Gamble 2A, an 89% chance to win nothing, and an 11% chance to win $1 million. Gamble 2B, a 90% chance to win nothing, and a 10% chance to win $5 million. Expected utility theory suggests that individuals should consistently prefer certain gambles across both experiments. However, many participants exhibit inconsistent preferences, preferring gamble 1A over 1B and gamble 2B over 2A, leading to a violation of the independence axiom inherent in expected utility theory. Psychological insights. Certainty effect. Individuals often overvalue certain outcomes, leading them to prefer guaranteed results over probabilistic ones, even when the expected value is lower. Zero effect. This concept suggests that people have an aversion to the possibility of receiving nothing, influencing their choices in scenarios involving zero-variance lotteries. Implications and criticisms. The Sorites Paradox has significant implications for economic theory, highlighting the need for models that account for observed deviations from rational decision-making. It has spurred the development of alternative theories, such as prospect theory, which better capture human behavior under risk and uncertainty. However, some scholars argue that the paradox does not necessarily invalidate expected utility theory, but suggests the necessity for a more nuanced utility function that incorporates psychological factors influencing decision-making. Rethinking rationality. The Sorites Paradox serves as a compelling reminder that human decision-making is complex and often defies traditional economic models. Recognizing these inconsistencies is crucial for developing more accurate theories that reflect actual human behavior, ultimately leading to better predictions and interventions in fields ranging from economics to public policy. The Ellsberg paradox, introduced by economist Daniel Ellsberg in 1961, exposes inconsistencies in expected utility theory by illustrating how individuals often prefer known risks over unknown ones, even when the latter might offer better outcomes. This behavior, termed ambiguity aversion, suggests that people have an inherent discomfort with uncertainty regarding probabilities. Exploring the paradox. The two-urn scenario. Ellsberg's seminal experiment presents two urns. Urn A contains 50 red and 50 black balls with known probabilities. Urn B contains 100 balls of red and black in unknown proportions. Participants are offered bets on drawing red or black balls from both urns. Expected utility theory suggests indifference between certain bets, e.g. red from urn A, and corresponding ambiguous bets, e.g. red from urn B. However, many participants prefer the known risk of urn A, revealing a preference for known probabilities over ambiguous ones. The one-urn scenario. In another setup, a single urn contains 90 balls, 30 red and 60 black or yellow, in unknown ratios. Participants choose between gambles involving red, black, yellow, or combinations thereof. Choices often violate expected utility predictions, further highlighting ambiguity aversion. Psychological underpinnings. The preference for known risks aligns with psychological theories. Ambiguity aversion, a tendency to favor options with known probabilities over those with unknown risks. Uncertainty reduction, seeking to minimize cognitive dissonance by avoiding situations with unpredictable outcomes. These tendencies influence decision-making beyond laboratory settings, affecting areas like insurance, investment, and health choices. Implications for decision theory. The Ellsberg paradox challenges the assumption of rational behavior under uncertainty. It suggests that models incorporating ambiguity aversion, such as Choquet expected utility and Max-Min expected utility, may better predict real-world decisions. Understanding these preferences is crucial for fields like economics, policymaking, and behavioral science. Real-world applications. Ambiguity aversion has practical implications. Financial investments. Investors often prefer domestic assets over foreign ones, even when returns and risks are comparable, due to familiarity and perceived lower ambiguity. Policy decision-making. policymakers may favor known policy outcomes over uncertain alternatives, potentially leading to suboptimal decisions when better options exist under ambiguity. Embracing ambiguity in decision-making. The Ellsberg paradox underscores the complexity of human decision-making under uncertainty. Recognizing and accounting for ambiguity aversion can lead to more accurate models and improved strategies in addressing real-world decisions involving risk and uncertainty. Jevons Paradox. The paradox unveiled. Formulated by British economist William Stanley Jevons in 1865, Jevons' paradox posits that enhancements in the efficiency of resource utilization can lead to an overall increase in resource consumption. This counterintuitive phenomenon occurs because improved efficiency often reduces the operational costs of using a resource, thereby stimulating greater demand and usage. Mechanisms and modern implications. Mechanisms behind the paradox. When a technology becomes more efficient, the cost per unit of service typically declines. For example, if a car's fuel efficiency improves, the cost of traveling a given distance decreases. This reduction in costs can lead individuals and businesses to increase their travel, thereby offsetting the initial energy savings. Consequently, the aggregate consumption of a resource may rise despite technological advancements aimed at reducing its use. Historical context and early observations. During the Industrial Revolution, Jevons observed that improvements in the efficiency of steam engines led to an increase in coal consumption. As engines became more efficient, the cost of operating them decreased, leading to their more widespread use and, paradoxically, greater total coal consumption. Contemporary examples. Artificial intelligence (AI) development. Recent advancements in AI, such as China's DeepSeek model, have significantly lowered the costs associated with developing AI applications. This reduction has made AI more accessible, leading to a surge in its adoption across various industries. However, this increased usage could result in higher overall demand for computational resources, exemplifying Jevons' paradox in the digital realm. Autonomous vehicles. The advent of self-driving cars promises enhanced fuel efficiency and safety. Yet the convenience and reduced perceived cost of travel may encourage people to drive more, potentially leading to increased total fuel consumption and road usage, thereby illustrating the paradox. Lighting technologies. The widespread adoption of energy-efficient LED lighting has led to a significant reduction in the energy required for illumination. However, this efficiency gain has been offset by increased usage, such as extended lighting hours and the proliferation of decorative lighting, resulting in a net increase in energy consumption. Water conservation technologies. In agricultural sectors, the implementation of efficient irrigation systems has led to increased water usage. Farmers, perceiving irrigation as less costly due to efficiency gains, have expanded irrigated areas and increased crop production, thereby consuming more water overall. Policy considerations. Understanding Jevons' paradox is crucial for formulating effective energy and environmental policies. Relying solely on efficiency improvements to reduce resource consumption may be insufficient. Policymakers often need to implement additional measures such as taxes, regulations, or incentives to curtail demand and achieve desired conservation outcomes. For example, implementing carbon taxes or setting emission caps can help counteract the rebound effect associated with efficiency gains. Strategic approaches to mitigate the paradox. To address the challenges posed by Jevons' paradox, a multifaceted approach is essential. Decoupling economic growth from resource consumption. Promoting business models that deliver services without a corresponding increase in resource use can help achieve sustainable development. Encouraging behavioral change. Educating consumers about the environmental impacts of their choices can lead to reduced demand for resource-intensive goods and services. Investing in renewable resources. Shifting from finite to renewable resources can alleviate the pressure on ecosystems and promote long-term sustainability. Implementing comprehensive policy frameworks. Governments can play a pivotal role by enacting policies that promote efficiency while also addressing the rebound effect. This includes setting stringent efficiency standards, providing incentives for low-resource products, and investing in public infrastructure that supports sustainable practices. Navigating the paradox. While technological advancements in efficiency offer numerous benefits, acknowledging the potential for increased consumption is essential. A comprehensive approach that combines efficiency improvements with strategic demand management policies is vital to ensure that resource conservation goals are met without unintended escalation in usage. By understanding and addressing the dynamics of Jevons paradox, societies can work towards sustainable development that harmonizes technological progress with environmental stewardship. Wigner's Friend Paradox. The essence of the paradox. Proposed by physicist Eugene Wigner in 1961, the Wigner's Friend Paradox delves into the perplexing nature of quantum measurement and observation. It challenges our understanding of reality by highlighting the discrepancies that arise when considering different observers within the quantum framework. Exploring the depths of quantum observation. The thought experiment. Imagine a scenario where Wigner's friend conducts a quantum measurement within a closed laboratory. According to quantum mechanics, the system being observed exists in a superposition of states until measured, at which point it collapses into one of the possible outcomes. From the perspective of the friend inside the lab, upon measurement, the system collapses to a definite state. However, from Wigner's external viewpoint, the entire laboratory, including the friend and the system, is in a superposed state until he learns the outcome of the measurement. This leads to a paradox. Both perspectives seem valid, yet they suggest conflicting realities regarding the state of the system. Implications for objective reality. This thought experiment raises fundamental questions about the nature of objective reality in quantum mechanics. If different observers can have contradictory accounts of the same event, it challenges the notion of a single, objective reality. The paradox suggests that consciousness and observation play crucial roles in determining the state of a quantum system, blurring the lines between subjective experience and objective existence. Extensions and modern interpretations. Building upon Wigner's original scenario, physicists Daniela Frotziger and Renato Renner in 2018 proposed an extended version of the paradox. They introduced multiple observers, each with their own measurements and perspectives, leading to even more complex contradictions. Their work suggests that standard interpretations of quantum mechanics may be incomplete or require modification to account for these inconsistencies. Debates and resolutions. The Wigner's Friend Paradox has sparked extensive debates among physicists and philosophers. Some argue that the paradox exposes limitations in our understanding of quantum mechanics, while others believe it highlights the need for a more nuanced interpretation of quantum theory. Various resolutions have been proposed, including the idea that consciousness causes wave function collapse, or that all possible outcomes coexist in a multiverse. However, no consensus has been reached, and the paradox continues to be a topic of active research and discussion. The ongoing quest for understanding. The Wigner's Friend Paradox remains a profound enigma in the field of quantum mechanics, challenging our perceptions of reality, observation, and the role of consciousness. As research progresses, it may eventually lead to a more comprehensive understanding of the quantum world and our place within it. Hume's problem of induction paradox. Formulated by the Scottish philosopher David Hume in his work A Treatise of Human Nature, 1739, the problem of induction challenges the rational basis of inductive reasoning. Inductive reasoning involves drawing general conclusions based on specific observations, such as inferring that the sun will rise tomorrow because it has risen every day in the past. Hume questioned the legitimacy of such inferences, suggesting that they lack a solid foundation. Delving deeper into inductive reasoning. The structure of inductive reasoning. Inductive reasoning allows us to form generalizations from particular instances. For example, observing that a woman walks her dog by the market at 8 a.m. on multiple Mondays might lead us to conclude that she consistently does so. However, Hume pointed out that no matter how many times we observe this pattern, it doesn't logically guarantee that the woman will continue this behavior in the future. Hume's critique, the circularity issue. Hume argued that justifying inductive inferences is problematic because any attempt to validate them either leads to circular reasoning or remains unsubstantiated. He presented a dilemma. Demonstrative arguments. These are logically certain and yield conclusions that are necessarily true. However, they don't provide information about the world. They are tautological and don't help in predicting future events based on past observations. Probable arguments. These are based on experience and aim to predict future occurrences. Yet, justifying them requires assuming that the future will resemble the past, which is itself an inductive inference, leading to circular reasoning. The underlying assumption, uniformity of nature. Central to inductive reasoning is the assumption that the future will mirror the past, a concept known as the uniformity of nature. Hume questioned the validity of this assumption, suggesting that there's no rational basis for believing that future events will necessarily resemble past ones. This skepticism challenges the very core of empirical science, which relies heavily on inductive inferences. Implications for science and daily life. The problem of induction has profound implications. Scientific methodology. Science depends on observing patterns and formulating laws based on repeated experiments. Hume's critique suggests that scientific laws are not derived from logical certainty, but are based on habitual belief in the uniformity of nature. Daily decision-making. In everyday life, we trust that patterns will continue, for instance, expecting that a well-maintained car will start reliably. Hume's problem invites us to reflect on the justification for such expectations. Responses and ongoing debate. Philosophers have proposed various responses to Hume's skepticism. Pragmatism. Some argue that despite its philosophical shortcomings, inductive reasoning is practically indispensable and yields sufficiently reliable results for everyday purposes. Probabilistic justifications. Others suggest that inductive inferences can be justified through probability theory, acknowledging uncertainty but providing a framework for making informed predictions. Rejection of inductive justification. Some, like Karl Popper, have proposed that science doesn't rely on induction but on falsification, where hypotheses are rigorously tested and potentially refuted. Embracing the uncertainty. David Hume's problem of induction continues to challenge our understanding of knowledge and reasoning. While inductive reasoning is foundational to human thought and scientific inquiry, its philosophical justification remains contentious. Acknowledging this issue encourages a more nuanced appreciation of the limitations and strengths of our reasoning processes. Problem of other minds paradox. The essence of the problem. The problem of other minds is a philosophical conundrum that questions how we can know that other beings possess minds and consciousness similar to our own. While we have direct access to our own thoughts and feelings, our knowledge of others' mental states is indirect, relying on observation and inference. This issue challenges the assumption that other people experience the world in ways akin to ourselves. Exploring the depths of the problem. Understanding the problem. At its core, the problem of other minds posits that, despite observing others' behaviors, we cannot directly access their subjective experiences. This leads to skepticism about the existence of other minds beyond our own. Philosopher Bertrand Russell addressed this by noting that the intelligent behaviors exhibited by others are similar to our own, suggesting that they too possess minds. Philosophical perspectives. The problem has been a subject of extensive discussion in both analytic and continental philosophical traditions. Some philosophers argue that our ability to attribute mental states to others is grounded in a theory of mind, an innate cognitive mechanism that allows us to infer others' thoughts and feelings. However, this ability is not without its challenges, as it relies on behavioral cues that may not always accurately reflect internal states. Solipsism, the extreme skeptical view. Solipsism is the philosophical idea that only one's own mind is sure to exist. While extreme, it highlights the difficulty in proving the existence of other minds. Even if we accept that others exhibit behaviors similar to ours, we cannot be certain that their experiences mirror our own. Practical implications. Despite philosophical skepticism, in daily life, we operate under the assumption that others have minds and feelings. This belief is foundational to social interactions, empathy, and communication. However, the problem of other minds invites us to reflect on the limits of our knowledge and the assumptions we make about others' experiences. Embracing the uncertainty. The problem of other minds remains a profound challenge in philosophy, prompting us to question the nature of consciousness and our knowledge of others. While we may never fully bridge the gap between our own subjective experiences and those of others, acknowledging this problem encourages humility and deeper inquiry into the mysteries of the mind. Continuum hypothesis paradox. The essence of the hypothesis. Formulated by mathematician George Cantor in the late 19th century, the continuum hypothesis, CH, addresses the nature of infinity within set theory. It posits that there is no set whose cardinality, size, is strictly between that of the integers and the real numbers. In other words, the cardinality of the continuum, the set of real numbers, is the next size up from the cardinality of the set of natural numbers, with no intermediate sizes. Delving deeper into the hypothesis. Cantor's revolution in set theory. Cantor's introduction of set theory transformed our understanding of infinity. He demonstrated that not all infinities are equal. Some are larger than others. Through his work, Cantor established a hierarchy of infinities, with the set of natural numbers representing the smallest infinity, termed Aleph null. The real numbers, however, form a larger infinity, known as the cardinality of the continuum. The CH questions whether there exists a cardinality between these two. The independence from Zermelo-Fraenkel set theory. A significant development in the study of CH came with Kurt Gödel and Paul Cohen's work in the 20th century. They showed that both the CH and its negation are consistent with the standard axioms of set theory, Zermelo-Fraenkel set theory, with the axiom of choice, abbreviated ZFC, provided these axioms themselves are consistent. This means that CH cannot be proven or disproven using the standard set-theoretic axioms, is independent of them. Implications for mathematics and philosophy. The independence of the CH has profound implications for mathematics and philosophy. It suggests that our intuitive understanding of infinity and the structure of the real number line may be more complex than previously thought. The existence of different sizes of infinity challenges our perceptions of continuity and discreteness, influencing areas such as analysis, topology, and the philosophy of mathematics. Recent developments and ongoing research. Contemporary research continues to explore the ramifications of the CH's independence. Some mathematicians investigate alternative set theories that might resolve the status of CH differently, while others examine the implications of CH's independence for the foundations of mathematics. For instance, certain models of set theory suggest that additional axioms could determine the truth or falsehood of CH, though no consensus has been reached. Embracing the infinite complexity. The continuum hypothesis remains a central topic in mathematical logic, symbolizing the intricate and often counterintuitive nature of infinity. Its independence from standard set-theoretic axioms challenges mathematicians to refine their understanding of mathematical structures and the infinite. As research progresses, the CH continues to inspire debate and exploration, reflecting the dynamic and evolving landscape of mathematical thought. Arrow's impossibility theorem, also known as social choice paradox. The essence of the theorem. Formulated by economist Kenneth Arrow in his 1951 book Social Choice and Individual Values, Arrow's impossibility theorem presents a fundamental challenge in the field of social choice theory. It asserts that no rank-order voting system can simultaneously fulfill a specified set of seemingly reasonable criteria when aggregating individual preferences into a collective decision. This result highlights inherent limitations in designing fair and rational voting mechanisms. Delving deeper into the theorem. The core criteria. Fairness in voting systems. Arrow identified several conditions that a fair voting system should satisfy. Unrestricted domain, universality. Every possible set of individual preferences should be allowed. Non-dictatorship. No single voter should have the power to always determine the group's preference. Parado efficiency, unanimity. If every voter prefers one option over another, the group's preference should reflect this. Independence of irrelevant alternatives. IIA, the group's preference between two options should not be affected by the introduction of a third, irrelevant option. Non-imposition, citizen sovereignty. Every possible societal preference order should be achievable, given some set of individual preferences. Arrow's theorem demonstrates that no voting system can satisfy all these conditions simultaneously when there are three or more options to choose from. This result implies that compromises are inevitable in any voting system, and some degree of fairness may be unattainable. Intuitive illustration, the voting paradox. Consider a scenario with three candidates, A, B, and C, and three voters with the following preferences. Voter 1 prefers A greater than B greater than C. Voter 2 prefers B greater than C greater than A. Voter 3 prefers C greater than A greater than B. Applying a majority rule to each pair of candidates leads to cyclical preferences. A is preferred over B. Voters 1 and 3 prefer A to B. B is preferred over C. Voters 1 and 2 prefer B to C. C is preferred over A. Voters 2 and 3 prefer C to A. This cycle, A greater than B greater than C greater than A, reveals a collective preference that is intransitive, challenging the notion of a clear societal choice. Implications for voting systems. Arrow's theorem has profound implications for the design of voting systems. Plurality systems. Systems like first-past-the-post often fail to meet fairness criteria, as they can lead to results that don't reflect the true preferences of the majority. Ranked choice voting. While aiming to address some issues, ranked choice methods are also susceptible to paradoxes highlighted by Arrow's theorem. Condorcet methods. These methods seek to identify a candidate who would win against every other candidate in head-to-head comparisons. However, they can result in cyclical preferences, similar to the example above. Beyond voting, broader applications. Arrow's theorem extends beyond electoral systems, influencing areas like collective decision-making in organizations and committees. Aggregating individual preferences into a group decision can be fraught with inconsistencies. Economic theory, understanding how individual preferences translate into market choices and social welfare considerations. Philosophy and ethics, debates about the nature of collective judgment and the challenges in achieving a fair consensus. Embracing the paradox. Arrow's impossibility theorem serves as a sobering reminder of the complexities inherent in collective decision-making. It underscores the challenges in designing systems that are simultaneously fair, rational, and representative of diverse individual preferences. Recognizing these limitations encourages ongoing exploration of alternative decision-making frameworks and a deeper understanding of the trade-offs involved in collective choices. Imagine for a moment that everything you know, your memories, your experiences, your very existence, is an illusion. What if you are nothing more than a fleeting, self-aware entity that spontaneously materialized from the chaotic void of the universe, complete with fabricated memories and perceptions? This unsettling thought experiment is at the heart of the Boltzmann brain paradox, a concept that challenges our understanding of reality, consciousness, and the nature of the universe itself. The Boltzmann brain paradox is rooted in the principles of thermodynamics and statistical mechanics, disciplines that study the behavior of systems with a large number of particles. In the late 19th century, Austrian physicist Ludwig Boltzmann sought to explain the apparent order and low entropy, a measure of disorder, observed in the universe. He proposed that the universe, over vast periods, naturally fluctuates between states of high and low entropy due to random thermal motions of particles. Occasionally, these fluctuations could lead to the spontaneous formation of ordered structures, such as stars, planets, or even conscious beings. Building upon Boltzmann's ideas, the paradox suggests that it is statistically more probable for a single self-aware entity, a Boltzmann brain, to emerge from random fluctuations than for an entire universe like ours to exist. This is because the spontaneous assembly of a solitary brain requires far fewer particles and a smaller decrease in entropy compared to the formation of a vast, organized cosmos. Consequently, if the universe were eternal and infinite, we would expect Boltzmann brains to vastly outnumber normal observers like ourselves. This leads to a profound philosophical dilemma. If Boltzmann brains are the most common form of consciousness in the universe, how can we be certain of our own experiences and perceptions? Could we be Boltzmann brains, spontaneously arisen with fabricated memories and sensations, existing momentarily before dissolving back into the cosmic chaos? This scenario challenges the very foundation of empirical knowledge and raises questions about the reliability of our observations and the scientific method. The Boltzmann brain paradox also intersects with modern cosmological theories, particularly those concerning the nature of the universe's expansion and the concept of the multiverse. Some cosmologists argue that in a universe undergoing eternal inflation, a state of perpetual exponential expansion, pocket universes with varying physical laws could emerge. Within this framework, the likelihood of Boltzmann brains appearing becomes a significant concern, as their prevalence could undermine the assumption that our observations reflect an objective external reality. To address this paradox, scientists have proposed several resolutions. One approach involves re-examining the assumptions about the universe's initial conditions and the mechanisms governing entropy. If the universe began in a state of exceptionally low entropy, the subsequent evolution could favor the emergence of complex structures and conscious beings like ourselves over Boltzmann brains. Another perspective suggests that our very ability to question our existence and observe the universe implies a level of coherence and continuity incompatible with the fleeting nature of Boltzmann brains. The Boltzmann brain paradox serves as a profound reminder of the complexities inherent in understanding consciousness, reality, and the cosmos. It challenges us to critically examine the assumptions underlying our perception of existence and the methodologies we employ to explore the universe. While the notion that we might be ephemeral, spontaneously formed brains is deeply unsettling, it also underscores the importance of continued inquiry and the pursuit of knowledge. By confronting such paradoxes, we not only deepen our comprehension of the universe, but also enrich our appreciation for the mysteries that define our place within it. Condorcet Paradox. Understanding the paradox. The Condorcet Paradox, named after the 18th century French philosopher and mathematician Marie-Jean-Antoine Nicolas de Caratat, Marquis de Condorcet, exposes a fundamental challenge in collective decision-making processes. It illustrates how individual preferences, when aggregated, can lead to collective choices that are inconsistent or cyclic, defying the notion of a clear societal preference. This paradox is particularly evident in voting systems where majority rule is applied to pairwise comparisons among alternatives. Delving deeper into the paradox. Mechanics of the Condorcet Paradox. To comprehend the Condorcet Paradox, consider a scenario with 3 voters and 3 alternatives. Voter 1 prefers alternative A greater than B greater than C. Voter 2 prefers alternative B greater than C greater than A. Voter 3 prefers alternative C greater than A greater than B. In pairwise comparisons, A versus B. Voters 1 and 3 prefer A over B. Voter 2 prefers B over A. Result: A is preferred over B by 2 out of 3 voters. B versus C. Voters 1 and 2 prefer B over C. Voter 3 prefers C over B. Result: B is preferred over C by 2 out of 3 voters. C versus A. Voters 2 and 3 prefer C over A. Voter 1 prefers A over C. Result: C is preferred over A by 2 out of 3 voters. This creates a cycle, A greater than B greater than C greater than A, demonstrating intransitive collective preferences. Such cycles pose significant challenges for voting systems aiming to reflect a coherent societal preference. Implications for voting systems. The occurrence of the Condorcet paradox has profound implications for the design and evaluation of voting systems. Majority rule limitations. While majority rule is intuitive, the paradox reveals its potential to produce inconsistent outcomes when voters' preferences are cyclic. Condorcet methods. These methods aim to identify a candidate who would win in all pairwise comparisons. However, the presence of cycles complicates the determination of a clear winner, as no candidate may consistently outperform all others. Strategic manipulation. Understanding the paradox is crucial for recognizing how voting systems can be susceptible to strategic voting, where individuals may misrepresent their preferences to influence outcomes. Real-world applications and examples. The Condorcet paradox is not merely a theoretical construct, it has practical implications. Political elections. In multi-candidate elections, voter preferences can lead to cycles, making it challenging to identify a candidate who truly represents the majority's preference. Committee decision-making. Groups making collective decisions may encounter cycles and preferences, leading to indecision or the need for additional decision-making rules to break the cycle. Public policy choices. policymakers must be aware of the paradox when designing mechanisms to aggregate public preferences, ensuring that policies enacted reflect a stable and consistent societal choice. Navigating the paradox. The Condorcet paradox underscores the complexities inherent in collective decision-making processes. It challenges the assumption that aggregating individual preferences will naturally lead to a consistent and rational collective choice. Recognizing this paradox is essential for developing voting systems and decision-making frameworks that strive to accurately and fairly represent the diverse preferences of a population. Ongoing research in social choice theory continues to explore mechanisms to mitigate the effects of such paradoxes, aiming to enhance the effectiveness and fairness of democratic processes. The paradox of self-amendment. Defining the paradox. The paradox of self-amendment arises when a legal system's foundational rules are employed to alter or amend those very rules, potentially leading to contradictions or inconsistencies. This situation is particularly pronounced when the rules governing change are themselves subject to modification under their own authority. The paradox challenges our understanding of legal authority, consistency, and the nature of systemic change. Unpacking the paradox. Legal frameworks and self-amendment. In many legal systems, constitutions or foundational legal documents include provisions detailing the process for their own amendment. This self-amendment mechanism allows the legal system to adapt over time. However, when the authority to amend is embedded within the document itself, questions arise about the legitimacy and limits of such changes. For instance, can a constitution unilaterally alter its own amendment procedures without external validation? Logical implications. Beyond the legal realm, the paradox touches on logical principles concerning self-reference and authority. When a rule is used to change itself, it can lead to logical conundrums about consistency and the nature of authority. This scenario mirrors certain logical puzzles where entities reference or alter themselves, leading to circular reasoning or contradictions. Philosophical perspectives. Philosophically, the paradox of self-amendment raises questions about omnipotence and the nature of change. Can an all-powerful entity limit its own power? This inquiry delves into discussions about the nature of authority, freedom, and the possibility of self-imposed constraints. The paradox invites contemplation on whether true self-amendment is possible or if it leads to inherent contradictions. Navigating the paradox. The paradox of self-amendment serves as a critical lens through which we can examine the interplay between law, logic, and philosophy. It challenges our assumptions about authority, consistency, and the mechanisms of change within systems. By exploring this paradox, we gain deeper insights into the complexities of legal frameworks, logical structures, and philosophical doctrines, fostering a more nuanced understanding of how systems evolve and adapt. Paradox of majority rule. Understanding the paradox. Majority rule is a foundational principle in democratic systems, positing that the preference of more than half of the participants should determine collective decisions. However, this seemingly straightforward concept harbors inherent paradoxes that challenge its efficacy and fairness. One prominent example is the Condorcet paradox, which reveals that individual rational preferences can aggregate into a collective irrational outcome. Delving deeper into the paradox. Mechanics of the Condorcet paradox. Consider a scenario with 3 voters and 3 alternatives, A, B, and C. Voter 1 prefers A greater than B greater than C. Voter 2 prefers B greater than C greater than A. Voter 3 prefers C greater than A greater than B. In pairwise comparisons, A versus B, voters 1 and 3 prefer A, voter 2 prefers B. Result, A is preferred over B by a 2:1 majority. B versus C. Voters 1 and 2 prefer B. Voter 3 prefers C. Result: B is preferred over C by a 2:1 majority. C versus A. Voters 2 and 3 prefer C. Voter 1 prefers A. Result: C is preferred over A by a 2:1 majority. This cycle, A greater than B greater than C greater than A, indicates intransitive collective preferences where the group lacks a clear majority preference despite individual rationality. Implications for democratic decision-making. The paradox underscores potential flaws in majority rule. Intransitivity. Collective preferences may be cyclic, leading to decision-making deadlocks. Agenda manipulation. The order of voting can influence outcomes, allowing strategic structuring to achieve desired results. Absence of a Condorcet winner. No option may emerge as the majority's consistent preference across all pairings. These theoretical issues manifest in practical scenarios. Political elections. In multi-candidate races, vote splitting can result in a winner without broad majority support. Legislative processes. Policy decisions can be swayed by the sequence of voting on amendments, reflecting the paradox's impact. Addressing the paradox. To mitigate these challenges, alternative voting systems have been proposed. Ranked choice voting. Voters rank candidates, allowing for instant runoffs and potentially more representative outcomes. Condorcet methods. These identify a candidate who can win all pairwise matchups, aiming to reflect true majority preference. Navigating majority rule complexities. The paradox of majority rule highlights that aggregating individual preferences doesn't always yield coherent, collective decisions. Recognizing and understanding this paradox is crucial for designing democratic processes that strive for fairness, consistency, and true representation of the populace's will. Thrift paradox. Defining the paradox. The paradox of thrift, a concept deeply rooted in Keynesian economics, posits that while individual saving is generally considered prudent, when adopted collectively, it can lead to adverse economic outcomes. This paradox suggests that increased saving across an economy can suppress aggregate demand, thereby reducing overall economic growth and, paradoxically, diminishing total savings. Exploring the paradox in depth. Historical context and origins. The notion that collective saving could be detrimental predates Keynes. As early as 1714, Bernard Mandeville's The Fable of the Bees hinted at this idea, suggesting that private vices, such as spending, could result in public benefits. John Maynard Keynes later formalized this concept in the 20th century, emphasizing that during economic downturns, increased saving could exacerbate recessions by further reducing demand. Mechanics of the paradox. At its core, the paradox of thrift revolves around the relationship between individual behavior and aggregate economic outcomes. Individual perspective. Saving is often viewed as a virtue, providing financial security and future consumption potential. Aggregate impact. When many individuals simultaneously increase their savings, overall consumption declines. This reduction in consumption leads businesses to experience decreased revenues, prompting them to cut back on production and employment. Consequently, national income falls, which can result in lower total savings than initially intended. Illustrative example. Consider a simplified economy where initial state, individuals spend a significant portion of their income, sustaining business revenues and employment. Increased saving. A collective decision to save more leads to reduce consumption. Businesses face declining sales, prompting layoffs and wage reductions. The resulting decrease in income means individuals have less to save, potentially nullifying the initial increase in savings. Criticisms and counterarguments. The paradox of thrift has been subject to various critiques. Price flexibility. Some economists argue that reduced demand leads to lower prices, which can stimulate consumption and restore equilibrium. However, Keynesians counter that prices and wages are often sticky, not adjusting quickly enough to prevent prolonged recessions. Savings and investment link. Critics suggest that increased savings provide more funds for investment, potentially leading to economic growth. Yet during downturns, businesses may be reluctant to invest due to pessimistic profit expectations, rendering the additional savings less effective. Open economy considerations. In a global context, one country's increased savings could finance investment abroad, mitigating domestic negative effects. Nonetheless, this doesn't address the paradox on a global scale, as not all countries can simultaneously be net exporters. Policy implications. Understanding the paradox of thrift has significant implications for economic policy. Fiscal stimulus. Governments can counteract reduced private consumption by increasing public spending, thereby sustaining aggregate demand. Monetary policy. Lowering interest rates can discourage excessive saving and encourage borrowing and spending. Public messaging. Encouraging a balance between saving and spending can help maintain economic stability. Balancing thrift and economic vitality. The paradox of thrift highlights a counterintuitive aspect of economics. Individual prudence in saving, when widespread, can lead to collective economic challenges. Recognizing this paradox is crucial for policymakers aiming to foster economic environments where both personal financial security and robust economic growth coexist harmoniously. In the microscopic realm of quantum mechanics, particles such as electrons do not have definite positions or velocities until observed. Instead, they are described by wave functions, mathematical constructs that encapsulate all possible states of a system. The nature of these wave functions has sparked intense debate among physicists. Do they represent real, physical entities, or are they merely abstract tools for predicting measurement outcomes? This question lies at the heart of understanding the fundamental principles governing our universe. Understanding the wave function. In quantum mechanics, the wave function, denoted as psi, is a complex-valued function that provides a complete description of a quantum system. The square of its absolute value, psi superscript 2, gives the probability density of finding a particle in a particular region of space at a given time. This probabilistic interpretation was introduced by Max Born in 1926, marking a departure from classical deterministic views. For systems with multiple particles, the wave function becomes a function of all particle positions and spins, reflecting the system's overall quantum state. The symmetry properties of the wave function, especially concerning identical particles, are crucial in determining the statistical behavior of particles, leading to the distinction between bosons and fermions. Interpretations of the wave function. The wave function's role has led to various interpretations regarding its physical reality. Copenhagen interpretation proposes that the wave function represents our knowledge of a system rather than the system's physical state itself. Upon measurement, the wave function collapses to a specific state, reflecting the transition from a superposition of possibilities to a single reality. Many worlds interpretation suggests that all possible outcomes of quantum measurements actually occur, each in its own separate universe. Here, the wave function never collapses. Instead, it continually evolves, encompassing all realities. Pilot wave theory, Bohmian mechanics, introduces hidden variables to restore determinism, asserting that particles have definite positions and velocities guided by a pilot wave. The wave function in this view is a real, physical field influencing particle dynamics. Objective collapse theories. propose that wave function collapse is a real, physical process triggered by certain conditions, such as gravity or complexity, suggesting that the wave function represents a physical entity that undergoes spontaneous reduction to a definite state. Quantum Bayesianism, QBism, interprets the wave function as a subjective state of knowledge or belief about a system, emphasizing the role of the observer in assigning probabilities to different outcomes. Philosophical and conceptual considerations. The debate over the wave function's reality raises profound philosophical questions about the nature of reality and observation. Measurement problem. How does the act of measurement cause the wave function to collapse, and what determines the outcome? Reality of the quantum world. Do quantum entities exist in definite states independent of observation, or is reality fundamentally probabilistic and observer-dependent? Determinism versus indeterminism. If the wave function represents all possible outcomes, does this imply a deterministic universe, or is indeterminacy intrinsic to nature? Nonlocality and entanglement. How does the instantaneous action at a distance, observed in entangled particles, reconcile with the principles of locality and causality? Implications for quantum computing and technology. Understanding the nature of the wave function has practical implications for emerging technologies. Quantum computing utilizes principles like superposition and entanglement, which are directly related to the behavior of wave functions, to perform computations beyond the capabilities of classical computers. Quantum cryptography relies on the principles of quantum mechanics, including the behavior of wave functions, to create secure communication channels that are theoretically immune to eavesdropping. The nature of the wave function remains one of the most intriguing and debated aspects of quantum mechanics. While it serves as a powerful tool for predicting experimental outcomes, its interpretation challenges our deepest intuitions about reality. As research advances and new experiments shed light on these quantum mysteries, our understanding of the wave function's true nature may eventually lead to a more complete and coherent picture of the universe at its most fundamental level. Productivity paradox. Defining the paradox. The productivity paradox refers to the observed phenomenon where significant investments in information technology, IT, and technological advancements do not correspond to expected gains in productivity at the macroeconomic level. This paradox became particularly evident in the United States during the 1970s and 1980s when, despite rapid developments in IT, productivity growth experienced a notable slowdown. The term was popularized by economist Robert Solow, who famously remarked, "You can see the computer age everywhere, but in the productivity statistics." Exploring the paradox in depth. Historical context and origins. During the mid-20th century, the United States and other developed nations witnessed rapid technological advancements, especially in computing and information systems. These innovations were expected to drive substantial productivity improvements across various industries. However, contrary to these expectations, productivity growth rates stagnated or even declined during this period, leading to the emergence of the productivity paradox. Mechanisms underpinning the paradox. Several hypotheses have been proposed to explain this paradox. Mismeasurement hypothesis. This theory suggests that traditional productivity metrics may not accurately capture the benefits of IT investments. For instance, improvements in quality, variety, or convenience resulting from technological advancements might not be reflected in standard productivity statistics. Implementation lag hypothesis. Technological innovations often require complementary investments in organizational restructuring, employee training, and process optimization. The benefits of IT investments may not materialize immediately, but could become evident over time as firms adapt to new technologies. Redistribution hypothesis. Some economists argue that IT benefits may lead to gains for individual firms without translating into broader economic productivity improvements. For example, a company might use technology to capture a larger market share without increasing overall industry productivity. Recent developments and the modern productivity puzzle. In the late 1990s and early 2000s, productivity growth experienced a resurgence, particularly in sectors like retail, wholesale, and finance, which heavily invested in IT. This led some to believe that the paradox had been resolved. However, from the mid-2000s onward, productivity growth slowed again, despite rapid advancements in technologies such as artificial intelligence, AI, and automation. This renewed slowdown has been termed the Productivity Paradox 2.0, or the Productivity Puzzle. Recent discussions highlight that while AI and other technologies are increasingly prevalent, their impact on productivity statistics remains limited. For instance, despite the widespread adoption of AI, recent UK productivity growth has stagnated at just 0.3% annually, echoing Solo's earlier observation about the computer age. Implications for future technological adoption. The persistence of the productivity paradox underscores the complexity of translating technological advancements into measurable productivity gains. It suggests that investments in technology alone are insufficient. Organizations must also focus on complementary factors such as organizational change, workforce skills development, and process innovation to fully realize the potential of new technologies. Navigating the productivity paradox. The productivity paradox serves as a reminder that the relationship between technology and productivity is neither straightforward nor guaranteed. As we continue to integrate advanced technologies like AI into various sectors, it is crucial to adopt a holistic approach that considers not only technological investments, but also the broader organizational and societal contexts in which these technologies operate. The absent-minded driver paradox. Defining the paradox. The absent-minded driver paradox illustrates the challenges faced by decision-makers who cannot recall past choices during a sequence of decisions. Introduced by Piccioni and Rubinstein in 1997, this paradox explores scenarios where an individual's inability to remember previous actions leads to conflicts between planned strategies and real-time decisions. Exploring the paradox in depth. Scenario description. Consider a driver who must decide at two indistinguishable intersections whether to exit or continue driving. First intersection. X exiting leads to a payoff of 0. Continuing leads to the second intersection. Second intersection. Y exiting yields a payoff of 4. Continuing results in a payoff of 1. The driver cannot distinguish between intersections X and Y and does not remember if they've already passed one. Decision-making conflict. The paradox arises from the driver's conflicting reasoning. Ex-ante strategy. Before starting, the driver plans to exit at the second intersection, Y, to maximize the payoff. In situ decision. At each intersection, unable to recall past actions, the driver might choose to exit immediately, fearing they are at Y, potentially missing higher payoffs. Implications and resolutions. This paradox challenges traditional decision theory, especially regarding imperfect recall. Some scholars argue for decision models where information sets do not contain multiple decision nodes on the same path, aiming to resolve such paradoxes. Broader significance. The absent-minded driver paradox underscores the complexities in decision-making processes with imperfect recall, prompting reevaluation of existing models and strategies to accommodate real-world scenarios where memory limitations impact choices. Imagine standing at the edge of a vast chasm, peering into the abyss, and wondering how such a profound gap came to be. In the realm of physics, this chasm exists between two fundamental scales, the Planck scale, where gravity reigns supreme, and the electroweak scale, governing the behavior of the Higgs boson and the weak force. The staggering disparity between these scales poses a profound puzzle, known as the hierarchy problem, challenging our understanding of the universe's fundamental laws. The hierarchy problem centers on the question: why is the weak force responsible for processes like radioactive decay so much stronger than gravity? This discrepancy becomes particularly puzzling when considering the mass of the Higgs boson, the particle associated with the Higgs field that imparts mass to other particles. Quantum corrections suggest that the Higgs mass should be much larger than observed unless there is an extraordinary degree of fine-tuning, a delicate balancing act between large numbers that cancels out these corrections. This fine-tuning appears unnatural and begs for a deeper explanation. The problem is not merely academic, it has practical implications for our understanding of the universe. For instance, the vast difference in strength between the weak force and gravity influences the behavior of stars, the formation of galaxies, and the evolution of the cosmos itself. Addressing the hierarchy problem could shed light on why the universe is structured the way it is, and whether there are deeper symmetries or principles yet to be discovered. Over the decades, physicists have proposed various solutions to this conundrum. One such approach involves the concept of supersymmetry, which posits a relationship between two basic classes of particles, bosons and fermions. Supersymmetry aims to address the hierarchy problem by introducing new particles that could cancel out the quantum corrections affecting the Higgs mass. However, despite extensive searches, no experimental evidence for supersymmetric particles has been found, leaving this solution in the realm of speculation. Another intriguing proposal involves the idea of extra dimensions. In this framework, our familiar three-dimensional space is augmented by additional spatial dimensions that are compactified or curled up at scales beyond current observational capabilities. The existence of these extra dimensions could provide a natural explanation for the weakness of gravity compared to other forces. By distributing gravitational strength across these extra dimensions, gravity's relative weakness in our observable universe could be understood. However, this hypothesis also faces challenges, particularly in reconciling with existing experimental data. The hierarchy problem also intersects with cosmological considerations. The cosmological constant problem, which questions why the energy density of the vacuum is so small yet non-zero, also points to a potential connection between quantum field theory and general relativity. Understanding how these vast differences in energy scales arise could provide insights into both the large-scale structure of the universe and the fundamental laws governing particle interactions. The hierarchy problem stands as a testament to the complexities and mysteries that permeate the fabric of our universe. It challenges physicists to look beyond the established theories and venture into realms that may fundamentally alter our understanding of reality. As research continues, each hypothesis and experiment brings us closer to unraveling the true nature of the forces that govern the cosmos, potentially leading to a more unified and profound comprehension of the laws of physics. The trolley problem. Defining the problem. The trolley problem is a thought experiment in ethics that presents a moral dilemma involving a runaway trolley. In its classic form, the scenario is as follows. Scenario: A trolley is headed towards 5 people tied to a track. You stand next to a lever that can divert the trolley onto another track, where 1 person is tied. The ethical question is whether to pull the lever, sacrificing 1 person to save 5, or to refrain from acting, resulting in the death of the 5 individuals. This dilemma challenges individuals to consider the moral implications of action versus inaction and the ethical principles guiding such decisions. Exploring the dilemma in depth. Philosophical implications. The trolley problem probes the conflict between 2 major ethical theories. Utilitarianism. This perspective advocates for actions that maximize overall happiness or well-being. From a utilitarian viewpoint, pulling the lever to save 5 lives at the expense of 1 is the morally correct choice, as it results in a net gain of 4 lives. Deontology. This approach emphasizes the importance of moral rules and duties over the consequences of actions. A deontologist might argue that intentionally causing harm to an individual, pulling the lever to redirect the trolley, is inherently wrong, regardless of the outcome. Empirical research and criticisms. Empirical studies have investigated how people respond to the trolley problem, revealing that approximately 90% of participants choose to pull the lever, thereby endorsing a utilitarian solution. However, critics argue that the scenario's artificiality limits its applicability to real-life moral decision-making. Some researchers contend that the trolley problem oversimplifies complex ethical situations, reducing them to binary choices that may not reflect the nuances of actual moral dilemmas. Modern applications. The trolley problem has gained renewed relevance in discussions about autonomous vehicles and artificial intelligence. Designers of self-driving cars face ethical decisions reminiscent of the trolley problem, such as programming vehicles to prioritize the safety of passengers versus pedestrians in unavoidable accident scenarios. Platforms like MIT's Moral Machine have collected public opinions on these issues, highlighting cultural differences in ethical preferences and the challenges of creating universally accepted guidelines for machine ethics. The enduring significance of the trolley problem. The trolley problem continues to serve as a valuable tool in moral philosophy, prompting critical examination of ethical theories and their practical applications. Its relevance extends beyond academic discourse, influencing contemporary debates on technology, law, and public policy, where decisions often involve complex trade-offs between competing moral principles. The paradox of hedonism. Defining the paradox. The paradox of hedonism, also known as the pleasure paradox, refers to the counterintuitive phenomenon where the deliberate pursuit of pleasure may lead to its own diminishment. In essence, individuals who focus exclusively on seeking pleasure often find it elusive, whereas those who engage in activities for their intrinsic value may experience pleasure as a byproduct. Exploring the paradox in depth. Philosophical perspectives. Several philosophers have addressed this paradox. Henry Sidgwick, the utilitarian philosopher Henry Sidgwick, noted that the pursuit of pleasure is self-defeating. Pleasure cannot be acquired directly. John Stuart Mill, in his autobiography, Mill observed that those who are happiest are not those who aim directly at happiness, but rather those who have their minds fixed on other objectives. He stated, "Ask yourself whether you are happy, and you cease to be so." Viktor Frankl, the psychiatrist and Holocaust survivor Viktor Frankl, asserted that happiness ensues as an unintended side effect of one's dedication to a cause greater than oneself, not from its direct pursuit. Psychological explanations. Psychologically, the paradox can be understood through the concept of self-consciousness. When individuals become overly focused on their own happiness, they may engage in constant self-monitoring, which can lead to anxiety and decreased well-being. Conversely, immersing oneself in meaningful activities can lead to flow states characterized by deep engagement and enjoyment, thereby fostering happiness indirectly. Practical implications. Understanding the paradox of hedonism has practical applications. Personal development, focusing on personal growth, relationships, and meaningful work can lead to greater happiness than the direct pursuit of pleasure. Therapeutic practices, therapies that encourage clients to engage in value-driven activities rather than solely seeking happiness, may be more effective in enhancing well-being. Public policy. Policymakers might focus on creating conditions that allow individuals to find meaning and purpose, rather than promoting pleasure-seeking behaviors. Navigating the paradox. The paradox of hedonism highlights a fundamental insight into human nature. Pleasure and happiness are often byproducts of engaging in meaningful, value-driven activities rather than goals that can be achieved through direct pursuit. Recognizing this paradox encourages a shift in focus from seeking pleasure to finding purpose, ultimately leading to a more fulfilling life. The black hole firewall paradox. Defining the paradox. The black hole firewall paradox, proposed by physicists Ahmed Almhiri, Donald Marolf, Joseph Boltzmann, and James Sully in 2012, presents a fundamental conflict between quantum mechanics and general relativity. It suggests that an observer falling into a black hole would encounter a high-energy firewall at the event horizon, contradicting the expectation that crossing this boundary would be uneventful. Exploring the paradox in depth. The underlying conflict. The paradox arises from the interplay of three principles. Unitarity. In quantum mechanics, information is preserved during evolution. Equivalence principle. General relativity posits that free-falling observers experience local physics akin to being in empty space. Quantum field theory in curved spacetime predicts entangled particle pairs at the event horizon, with one escaping as Hawking radiation and the other falling into the black hole. For an old black hole nearing evaporation, new Hawking radiation must be entangled with both the infalling particles and previous radiation, violating the monogamy of entanglement principle. This inconsistency suggests that one of the foundational principles must be reconsidered. The firewall hypothesis. To resolve this, the firewall hypothesis proposes that the entanglement between infalling and outgoing particles is broken, releasing significant energy and creating a firewall at the event horizon. This implies that an infalling observer would encounter extreme conditions, challenging the equivalence principle. Alternative resolutions. Several theories have been proposed to address the paradox without invoking firewalls. Information loss, accepting that information is lost in black holes, violating unitarity. Modified quantum field theory, suggesting gradual loss of entanglement, avoiding abrupt firewalls. ER equals EPR conjecture, proposing that entangled particles are connected by wormholes, preserving entanglement without conflict. Fuzzball model, replacing the classical black hole with a quantum fuzzball, eliminating the traditional event horizon and associated paradoxes. The quest for resolution. The black hole firewall paradox remains unresolved, highlighting the need for a theory that unifies quantum mechanics and general relativity. Ongoing research continues to explore these foundational issues, aiming to deepen our understanding of the universe's most extreme environments. The Ship of Theseus paradox is a thought experiment that delves into questions of identity and change. It challenges our understanding of whether an object remains fundamentally the same when all its components are replaced over time. Originating from ancient Greek philosophy, this paradox continues to intrigue scholars and thinkers. The thought experiment. Imagine a ship owned by Theseus, the mythical king of Athens. Over time, as each part of the ship decays, it is replaced with a new, identical component. This process continues until every single part of the ship has been replaced. The central question arises, is this still the original ship of Theseus, or has it become a new entity? Historical context. The earliest mention of this paradox comes from Plutarch, who used it to explore the nature of identity and persistence. He described how the Athenians maintained Theseus's ship by replacing decayed planks with new timber, raising the question of whether the ship remained the same after all parts were replaced. Centuries later, philosopher Thomas Hobbes extended the thought experiment by introducing a scenario where the removed wooden parts were gathered and reassembled into a new ship. This led to further contemplation about which, if either, of the ships could be considered the original. Philosophical implications. The ship of Theseus paradox raises several philosophical questions. Material constitution versus identity. Does an object's identity depend on the material it is made of, or is it defined by its form and function? Continuity and change. How do we reconcile the continuous identity of an object amidst constant change and replacement of its parts? Temporal persistence. At what point, if any, does an object cease to be itself due to cumulative changes over time? Proposed resolutions. Philosophers have proposed various solutions to address the paradox. Constitution is not identity. This perspective suggests that the material out of which an object is made is distinct from the object itself. Therefore, replacing all parts does not change the object's identity. Temporal parts theory, proposed by philosopher David Lewis. This theory posits that objects are extended in time and consist of temporal parts. Each time slice of the object is a distinct part, and the object's identity is a series of these temporal parts. Cognitive science perspective. Some scholars argue that the paradox arises from human cognitive biases, suggesting that our intuitions about object identity may not align with the complexities of the physical world. This view posits that the confusion stems from our mental constructs rather than the nature of the object itself. Deflationism. This view holds that debates about the identity of objects like the ship of Theseus are merely verbal disputes, stemming from different uses of the term identity, rather than substantive disagreements. Gradual replacement view. This perspective suggests that as long as the replacement of parts occurs gradually, maintaining functional continuity, the object retains its identity. However, if all parts are replaced simultaneously, it would be considered a new object. Bundle theory. This theory proposes that objects are merely collections, bundles, of their properties. If all properties, parts, change, the object is no longer the same. No change view. Some argue that as long as the form and function of the object remain consistent, it retains its identity, regardless of the replacement of individual parts. Real-world applications and analogies. The ship of Theseus paradox has practical applications in various fields. Personal identity. It parallels questions about human identity, such as whether a person remains the same despite physical and psychological changes over time. Artificial intelligence. In the realm of AI, if a machine's components are gradually replaced or upgraded, does it remain the same entity? Organizational identity. Businesses and institutions often undergo changes in personnel and structure. The paradox prompts questions about their continued identity. The ship of Theseus paradox remains a compelling exploration of how we perceive identity and change. It challenges our intuitions and encourages deeper reflection on the nature of objects and their persistence over time. While various philosophical perspectives offer differing resolutions, the paradox continues to stimulate discussion and inquiry into the fundamental aspects of existence and identity. The liar paradox is a classic conundrum in philosophy and logic that challenges our understanding of truth and reference. It arises from statements that refer to themselves in a contradictory manner, leading to logical dilemmas that have intrigued scholars for centuries. Origin and classical formulation. The paradox traces its roots to ancient Greece, attributed to Epimenides, a Cretan philosopher who purportedly stated, "All Cretans are liars." If Epimenides, himself a Cretan, is truthful, then his declaration implies that all Cretans lie, including himself, which leads to a contradiction. A more direct example is the statement, "This sentence is false." If the sentence is true, then it must be false as it claims, but if it's false, then it must be true, creating an endless loop of contradiction. The liar paradox has significantly influenced the development of formal logic and the philosophy of language. Kurt Gödel's first incompleteness theorem, for instance, employs a liar-like sentence to demonstrate that within any sufficiently powerful axiomatic system, there exist true statements that are unprovable within the system. This result underscores inherent limitations in formal mathematical systems and highlights the complexities introduced by self-referential statements. Additionally, the paradox has inspired alternative logical frameworks, such as para-consistent logics, which tolerate contradictions without leading to logical explosion, thereby offering a more nuanced approach to reasoning in the presence of paradoxical statements. These developments illustrate the profound impact of the liar paradox on both theoretical and applied aspects of logic and computation. Philosophical and logical implications. The liar paradox exposes limitations in classical two-valued logic, where statements are either true or false. It suggests that self-referential statements can defy such binary classifications, prompting the need for more nuanced logical frameworks. This paradox has influenced various fields, including mathematics and computer science, highlighting the complexities of self-reference and truth. Modern approaches and resolutions. To address the paradox, scholars have developed alternative logical systems. Hierarchical solutions. These involve organizing statements into levels, where statement about truth belongs to a higher level than the statements it describes, thereby avoiding self-reference. Para-consistent logics. These allow for contradictions to exist without collapsing the entire logical system, accommodating statements that can be both true and false. Dialetheism. This approach accepts that some statements are both true and false, embracing the paradox as a legitimate aspect of reality. Real-world applications and analogies. The liar paradox extends beyond theoretical discourse, influencing practical domains. Computer science. In programming, self-referential code can lead to infinite loops or undefined behaviors, mirroring the paradox's implications. Artificial intelligence. Developing AI that can navigate self-referential statements requires sophisticated logic to prevent contradictions and ensure reliable reasoning. Linguistics. Understanding how languages handle self-reference aids in parsing and interpreting complex sentence structures. Embracing the complexity of truth. The liar paradox remains a profound testament to the complexities inherent in language, logic, and truth. It challenges our foundational assumptions and encourages the exploration of more sophisticated systems to accommodate the nuances of self-reference and contradiction. By acknowledging and studying such paradoxes, we deepen our comprehension of logical frameworks and the intricate nature of human reasoning. Holographic principle paradox. Understanding the holographic principle. The holographic principle is a theoretical framework in physics proposing that all information contained within a volume of space can be described by data on its boundary. This concept suggests that our three-dimensional universe might be understood as a two-dimensional projection, similar to a hologram. Originally proposed by Gerard T. Hooft and later expanded by Leonard Susskind, the principle has profound implications for understanding black holes and the nature of the universe. Addressing the black hole information paradox. The black hole information paradox. Stephen Hawking's work in the 1970s introduced the concept of Hawking radiation, where black holes emit radiation due to quantum effects near the event horizon. This radiation leads to the gradual evaporation of black holes. However, Hawking suggested that this radiation is purely thermal and does not carry information about the matter that fell into the black hole, implying that information is lost from the universe, a notion conflicting with the principles of quantum mechanics, which assert that information must be preserved. Holographic principle as a resolution. The holographic principle offers a potential resolution to this paradox by proposing that all information about the matter inside a black hole is encoded on its event horizon. This means that as a black hole emits Hawking radiation and loses mass, the information about the infalling matter is not lost but rather stored on the surface, preserving the principles of quantum mechanics. Add/CFT correspondence. A significant realization of the holographic principle is the anti-de Sitter/conformal field theory, add/CFT, correspondence, formulated by Juan Meldacena. This duality suggests that a gravitational theory in a higher dimensional add space can be described by a lower dimensional conformal field theory on its boundary. This correspondence has provided insights into how information might be preserved in black holes, aligning with the predictions of the holographic principle. The broader implications. The holographic principle not only addresses the black hole information paradox, but also challenges our understanding of space, time, and the fundamental nature of reality. By suggesting that our universe might be a holographic projection, it opens new avenues for exploring the connections between gravity, quantum mechanics, and information theory. Quantum Zeno paradox. The quantum Zeno paradox refers to a counterintuitive phenomenon in quantum mechanics where systems' evolution can be inhibited or frozen due to frequent observations. This effect draws a parallel to Zeno's classical paradoxes, particularly the arrow paradox, which suggests that a flying arrow is motionless at any single instant in time. In the quantum realm, this translates to the idea that continuous measurement can prevent a quantum system from changing its state. Exploring the paradox in depth. Theoretical foundations. The paradox was first theoretically proposed by B. Mishra and E.C.G. Sudarshan in 1977. They demonstrated that an unstable particle, if continuously observed to see whether it decays, will never be found to decay. This implies that the act of measurement itself can hinder the natural evolution of a quantum system. Mechanism of the quantum Zeno effect. In quantum mechanics, the state of a system evolves over time according to the Schrödinger equation. However, when a measurement is performed, the system's wave function collapses to an eigenstate corresponding to the observed outcome. If measurements are made in rapid succession, the system repeatedly collapses to the same state, effectively suppressing its evolution. This phenomenon is known as the quantum Zeno effect. Experimental observations. The quantum Zeno effect has been experimentally observed in various systems. Atomic systems. Experiments have shown that the decay of excited atomic states can be inhibited by frequent observations, aligning with the predictions of the quantum Zeno effect. Photon polarization. Studies involving the polarization states of photons have demonstrated that rapid measurements can prevent changes in polarization, effectively freezing the photon state. Implications and applications. The quantum Zeno effect has significant implications. Quantum computing, understanding and controlling the quantum Zeno effect is crucial in quantum computing, where maintaining coherence and preventing decoherence are essential for reliable operation. Quantum control. The effect provides a mechanism for controlling quantum systems by manipulating the frequency of measurements, offering potential applications in quantum information processing and precision measurements. Criticisms and alternative interpretations. Some interpretations challenge the traditional understanding of the quantum Zeno effect. Measurement disturbance. Critics argue that the inhibition of evolution may result from a disturbance caused by measurement rather than the act of observation itself. Finite measurement intervals. In practical scenarios, measurements cannot be truly continuous, but occur at finite intervals, leading to debates about the applicability of the quantum Zeno effect in real-world systems. The paradox's role in quantum mechanics. The quantum Zeno paradox highlights the profound impact of observation in quantum mechanics, challenging classical intuitions about measurement and evolution. It underscores the necessity of rethinking concepts like time, change, and observation when dealing with quantum systems, offering deeper insights into the nature of reality at the microscopic scale. Lottery paradox. Introduced by philosopher Henry E. Keiber, Jr. in 1961, challenges our understanding of rational belief in the context of probability. It illustrates a conflict between the high probability of individual events and the certainty of a collective outcome, questioning how we justify beliefs based on probabilistic reasoning. Exploring the paradox in depth. The structure of the paradox. Consider a fair lottery with 1,000 tickets where exactly one ticket will win. For any given ticket, the probability of losing is 0.999, making it rational to believe that any specific ticket will not win. Applying this reasoning to all tickets leads to the belief that none will win, contradicting the certainty that one ticket must win. Principles leading to the paradox. The paradox arises from three seemingly reasonable principles. High probability acceptance. It is rational to accept a proposition with a very high probability of being true. Avoidance of inconsistency. It is irrational to accept propositions known to be inconsistent. Closure under conjunction. If it is rational to accept two propositions individually, it is rational to accept their conjunction. In the lottery scenario, accepting that each ticket will lose, based on high probability, and combining these beliefs leads to an inconsistency, as it contradicts the certainty that one ticket will win. Implications for epistemology. The lottery paradox has significant implications for epistemology, particularly concerning the nature of knowledge and rational belief. Rational acceptance. The paradox challenges the notion that high probability alone justifies rational belief, suggesting that additional criteria are necessary. Consistency in belief systems. It highlights the difficulty of maintaining consistency when aggregating individually rational beliefs, especially in probabilistic contexts. Knowledge and skepticism. The paradox raises questions about the threshold for knowledge, as accepting highly probable propositions may still lead to contradictions, fueling skeptical arguments. Proposed resolutions. Several approaches have been proposed to resolve the lottery paradox. Rejecting closure under conjunction. Some suggest that rational belief is not necessarily closed under conjunction, meaning accepting individual propositions does not compel acceptance of their conjunction. Probabilistic acceptance thresholds. Others propose setting a higher threshold for rational acceptance than mere high probability, requiring near certainty. Contextualism. This approach suggests that the standards for rational belief vary depending on the context, allowing for flexibility in handling such paradoxes. The paradox's role in philosophical inquiry. The lottery paradox serves as a pivotal challenge in understanding rational belief and probability. It compels philosophers to re-examine the criteria for justified belief and the principles governing rational acceptance, contributing to ongoing debates in epistemology and the philosophy of probability. Imagine possessing the ability to traverse the corridors of time, journeying to eras long past or distant futures. While this concept has captivated human imagination for centuries, it also gives rise to perplexing conundrums that challenge our understanding of causality and existence. Two of the most intriguing are the grandfather paradox and the Bootstrap paradox, both of which underscore the complexities inherent in the notion of time travel. The grandfather paradox, a twist in the fabric of causality. The grandfather paradox presents a scenario where a time traveler journeys to the past with the intent to prevent their own existence. A classic illustration involves a traveler who goes back in time and inadvertently causes the death of their grandfather before the traveler's parent is conceived. This act would render the traveler's birth impossible, creating a logical contradiction. If the traveler was never born, how could they have traveled back in time to commit the act? This paradox challenges our conventional understanding of cause and effect, suggesting that altering past events could lead to self-contradictory outcomes. While some theories propose that such paradoxes could be resolved through mechanisms like parallel universes or self-consistency principles, no definitive solutions have been universally accepted. The Bootstrap paradox, the enigma of self-causation. The Bootstrap paradox, also known as an ontological paradox, involves a scenario where an item or piece of information exists without a clear point of origin, creating a causal loop that defies logical explanation. A popular example is the story of a time traveler who gives Shakespeare a copy of his own works. Shakespeare publishes them, and the time traveler later reads them, travels back in time, and gives them to Shakespeare, perpetuating the cycle. In this loop, the works exist without ever being truly created, posing the question, who is the original author? This paradox challenges our notions of authorship, creativity, and the flow of information, suggesting that time travel could lead to scenarios where objects or knowledge exist without a discernible origin. Such situations provoke deeper philosophical inquiries about the nature of existence and the fabric of reality itself. Time travel, while a staple of science fiction, presents profound challenges to our understanding of time, causality, and the universe. Paradoxes like the grandfather and Bootstrap paradoxes highlight the intricate and often perplexing implications of altering the temporal continuum. As we continue to explore these concepts, both in theoretical physics and philosophical discourse, we are reminded of the delicate balance that underpins the reality we experience and the potential consequences of tampering with the threads of time. Consider the ticking of a clock, each second slipping away, marking the relentless march of time. Yet, when we delve into the fundamental nature of time, we encounter paradoxes that challenge this intuitive flow. Philosopher J.M.E. McTaggart, in his early 20th century work, argued that our perception of time involves a contradiction, suggesting that time itself might be an illusion. McTaggart introduced two perspectives to analyze time. The A-series. This perspective views events as moving from future to present to past, capturing our everyday experience of time's passage. The B-series. Here, events are ordered based on a fixed relation of earlier than or later than, without any flow from future to past. McTaggart argued that while the A-series is essential for expressing change, it leads to contradictions, implying that our perception of time's passage might be incoherent. He suggested that if time involves both the A series and the B series, it leads to a contradiction, and thus, time is unreal. This paradox challenges our conventional understanding of cause and effect, suggesting that altering past events could lead to self-contradictory outcomes. While some theories propose that such paradoxes could be resolved through mechanisms like parallel universes or self-consistency principles, no definitive solutions have been universally accepted. Further complicating our understanding, physicist Stephen Wolfram proposes that our experience of time arises from the interplay between our computational limitations as observers and the computational irreducibility of underlying processes. This perspective suggests that time emerges from more fundamental, timeless rules, challenging our conventional notions of temporal flow. Wolfram's view posits that if we were not computationally bounded, we could perceive the entire future instantly, eliminating the need for a concept of time. Conversely, if there weren't underlying processes with computational irreducibility, there would be no progressive unfolding of events, and thus no experience of time passing. This interplay gives rise to the flow of time that we perceive. Moreover, Wolfram suggests that the directionality of time, often associated with the second law of thermodynamics, emerges from this interplay. The increase in entropy or disorder aligns with our perception of time moving forward, reinforcing the concept of a flowing time. The nature of time remains one of the most profound and perplexing mysteries in both philosophy and physics. Paradoxes like McTaggart's and Wolfram's insights invite us to reconsider our intuitive understanding of time, suggesting that it may not be a fundamental aspect of reality, but rather an emergent phenomenon rooted in deeper, timeless processes. As we continue to explore these concepts, we edge closer to unraveling the true essence of time and its role in the fabric of the universe. The paradox of analysis. Understanding the paradox. The paradox of analysis, also known as the Langford-Moore paradox, presents a significant challenge in the philosophy of language and logic. Formulated by philosopher G. Moore in his work Principia Ethica and later named by C. H. Langford, the paradox explores the tension between two essential criteria for a conceptual analysis: correctness and informativeness. Delving deeper into the paradox. Conceptual analysis, definition and expectations. Conceptual analysis involves explicating the meaning of a concept by elucidating its necessary and sufficient conditions. The goal is to provide a deeper understanding of the concept's essence, often by expressing it through more fundamental or familiar terms. For an analysis to be deemed correct, it must accurately capture the original concept's meaning, ensuring that the analyzed concept and the original are interchangeable in all contexts without altering the intended meaning. However, for an analysis to be informative, it should convey new knowledge, offering insights that were not previously apparent. This becomes problematic when the analysis is correct but yields no new information, as the analysis merely restates what is already known. Conversely, if the analysis provides new information but is not correct, it misrepresents the original concept, leading to misunderstandings. Illustrative example: analyzing brother. Consider the attempt to analyze the concept of a brother by stating that a brother is a male sibling. While this analysis is correct in that it accurately defines a brother, it lacks informativeness. For someone unfamiliar with the term brother, this analysis does not provide additional understanding beyond the original concept. This illustrates how a correct analysis can be uninformative, failing to enhance comprehension. Philosophical implications. The paradox raises critical questions about the nature of philosophical analysis and the objectives it aims to achieve. It challenges the assumption that all correct analyses are inherently informative, suggesting that informativeness requires more than mere correctness. This has led to debates about the role of analysis in philosophy, with some philosophers questioning its utility if it cannot simultaneously be correct and informative. Proposed solutions and ongoing debates. Several approaches have been proposed to resolve the paradox. Reconceiving analysis. Some suggest redefining analysis to focus on linguistic definitions rather than conceptual elucidation, emphasizing the role of language in shaping understanding. Accepting uninformative analyses. Another perspective is to acknowledge that some analyses, while correct, may be inherently uninformative, and that informativeness is not a necessary criterion for all analyses. Rejecting conceptual analysis. Philosophers like Willard Van Orman Quine have proposed abandoning the notion of conceptual analysis altogether, arguing that it is a flawed endeavor that does not yield meaningful insights. The paradox's enduring significance. The paradox of analysis continues to be a focal point of philosophical inquiry, prompting ongoing discussions about the objectives and methods of conceptual analysis. It underscores the complexity of achieving analyses that are both correct and informative, challenging philosophers to refine their approaches to understanding and explaining concepts. By grappling with this paradox, the philosophical community gains deeper insights into the nature of knowledge, language, and the processes by which we come to understand the world around us. Meno's paradox, or paradox of inquiry. Defining the paradox. Meno's paradox, also known as the paradox of inquiry, originates from Plato's dialogue Meno. In this work, Meno questions Socrates about the feasibility of acquiring knowledge, leading to a philosophical conundrum. How can one search for knowledge of something entirely unknown, and even if found, how can one recognize it as the sought-after knowledge? Delving deeper into the paradox. The structure of the paradox. Meno presents Socrates with a dilemma. Searching for known knowledge. If one already knows what they are seeking, there's no need to search. They can directly access the information. Searching for unknown knowledge. If one doesn't know what they're seeking, they wouldn't know what to look for, making the search futile. This dichotomy suggests that inquiry is either unnecessary or impossible, challenging the very notion of learning and discovery. Socrates' response, theory of recollection. Socrates counters Meno's paradox by introducing the theory of recollection and amnesis. Innate knowledge. The soul is immortal and has acquired all knowledge in previous lifetimes. Learning as recollection. Learning is the process of recalling knowledge already possessed but forgotten, not the acquisition of new information. To illustrate this, Socrates engages a slave boy in a geometric problem, guiding him to rediscover knowledge he seemingly never learned. This demonstration aims to show that individuals can access latent knowledge through proper inquiry. Implications for epistemology. Meno's paradox and Socrates' theory raise significant questions about knowledge acquisition. Nature of knowledge. What constitutes true knowledge, and how do we distinguish it from mere belief? Possibility of learning. Can genuine learning occur, or is it merely the recollection of pre-existing knowledge? Methodology of inquiry. What methods can facilitate the discovery or recollection of knowledge, and how do we recognize valid knowledge when encountered? Modern perspectives and criticisms. Contemporary philosophers have debated the validity of Meno's paradox. Partial knowledge approach. Some argue that individuals possess fragments of knowledge that guide their inquiry, making learning a process of connecting these fragments. Critique of recollection. Others question the notion of innate knowledge, suggesting that learning is the acquisition of new information rather than the recollection of the old. True belief versus knowledge. the distinction between true belief and knowledge is explored, emphasizing that while beliefs can be true, they may lack the justification that constitutes knowledge. The enduring enigma of inquiry. Meno's paradox continues to influence philosophical discourse on epistemology, prompting ongoing exploration into the nature of knowledge, learning, and the processes by which we come to understand the world around us. It challenges assumptions about innate knowledge and the feasibility of genuine learning, encouraging deeper reflection on how we acquire and recognize knowledge throughout our lives. Hume's problem of induction paradox. Formulated by the Scottish philosopher David Hume in his work A Treatise of Human Nature, 1739, the problem of induction challenges the rational basis of inductive reasoning. Inductive reasoning involves drawing general conclusions based on specific observations, such as inferring that the sun will rise tomorrow because it has risen every day in the past. Hume questioned the legitimacy of such inferences, suggesting that they lack a solid foundation. Delving deeper into inductive reasoning. The structure of inductive reasoning. Inductive reasoning allows us to form generalizations from particular instances. For example, observing that a woman walks her dog by the market at 8 a.m. on multiple Mondays might lead us to conclude that she consistently does so. However, Hume pointed out that no matter how many times we observe this pattern, it doesn't logically guarantee that the woman will continue this behavior in the future. Hume's critique. The circularity issue. Hume argued that justifying inductive inferences is problematic because any attempt to validate them either leads to circular reasoning or remains unsubstantiated. He presented a dilemma. Demonstrative arguments. These are logically certain and yield conclusions that are necessarily true. However, they don't provide information about the world. They are tautological and don't help in predicting future events based on past observations. Probable arguments. These are based on experience and aim to predict future occurrences. Yet, justifying them requires assuming that the future will resemble the past, which is itself an inductive inference, leading to circular reasoning. The underlying assumption. Uniformity of nature. Central to inductive reasoning is the assumption that the future will mirror the past, a concept known as the uniformity of nature. Hume questioned the validity of this assumption, suggesting that there's no rational basis for believing that future events will necessarily resemble past ones. This skepticism challenges the very core of empirical science, which relies heavily on inductive inferences. Implications for science and daily life. The problem of induction has profound implications. Scientific methodology. Science depends on observing patterns and formulating laws based on repeated experiments. Hume's critique suggests that scientific laws are not derived from logical certainty, but are based on habitual belief in the uniformity of nature. Daily decision-making. In everyday life, we trust that patterns will continue, for instance, expecting that a well-maintained car will start reliably. Hume's problem invites us to reflect on the justification for such expectations. Responses and ongoing debate. Philosophers have proposed various responses to Hume's skepticism. Pragmatism. Some argue that despite its philosophical shortcomings, inductive reasoning is practically indispensable and yields sufficiently reliable results for everyday purposes. Probabilistic justifications. Others suggest that inductive inferences can be justified through probability theory, acknowledging uncertainty but providing a framework for making informed predictions. Rejection of inductive justification. Some, like Karl Popper, have proposed that science doesn't rely on induction but on falsification, where hypotheses are rigorously tested and potentially refuted. Embracing the uncertainty. David Hume's problem of induction continues to challenge our understanding of knowledge and reasoning. While inductive reasoning is foundational to human thought and scientific inquiry, its philosophical justification remains contentious. Acknowledging this issue encourages a more nuanced appreciation of the limitations and strengths of our reasoning processes. The Singularity Paradox. Defining the technological singularity. The technological singularity refers to a hypothetical point in the future when technological growth becomes uncontrollable and irreversible, resulting in unforeseeable changes to human civilization. This concept suggests that artificial intelligence, AI, will surpass human intelligence, leading to rapid advancements beyond our comprehension or control. The term singularity draws an analogy to the gravitational singularity at the center of black holes, where conventional laws of physics break down. Analyzing the paradox and its dimensions. Theoretical foundations of the singularity. Proponents of the singularity, such as futurist Ray Kurzweil, argue that technological progress follows an exponential growth curve, particularly in fields like computing power, data storage, and network connectivity. Kurzweil's law of accelerating returns posits that each technological advancement builds upon the previous one, leading to rapid and continuous innovation. Philosophical and ethical considerations. The prospect of superintelligent AI raises profound philosophical and ethical questions. Nature of consciousness. If machines achieve human-like intelligence, what does this imply about consciousness and self-awareness? Moral agency. Would superintelligent AI possess moral agency, and how would we assign ethical responsibility for its actions? Human identity. How would the existence of entities more intelligent than humans affect our understanding of human nature and our place in the world? Economic and social impacts. The advent of AI surpassing human intelligence could lead to significant economic and social upheavals. Labor market disruption. Automation of complex tasks could render many human jobs obsolete, leading to widespread unemployment and economic inequality. Wealth concentration. The entities controlling advanced AI technologies might amass unprecedented wealth and power, exacerbating social divisions. Policy challenges. Governments would face difficulties in regulating AI development and mitigating its societal impacts, especially if technological growth outpaces legislative processes. Risk of existential threats. Some scholars and technologists warn that the singularity could pose existential risks. Loss of control. Superintelligent AI might operate beyond human oversight, making decisions that are misaligned with human values and interests. Autonomous weaponry. Advanced AI could be used to develop autonomous weapons systems, potentially leading to unintended escalations and conflicts. Ethical misalignment. If AI systems are not properly aligned with human ethics, their actions could result in harm or the pursuit of goals detrimental to humanity. Critiques and alternative perspectives. Critics of the singularity concept offer several counterarguments. Technological plateau. Some theorists suggest that technological growth may eventually plateau due to physical, economic, or societal constraints, preventing the realization of a singularity. Complexity barriers. Developing AI with human-like general intelligence may encounter insurmountable technical challenges, limiting progress in that direction. Human-AI collaboration. Rather than a scenario where AI surpasses and replaces human intelligence, some envision a future of collaborative coexistence where AI augments human capabilities. Mitigation strategies and governance. Addressing the potential challenges of the singularity requires proactive measures. Ethical AI development. Establishing frameworks for the ethical design and deployment of AI, ensuring alignment with human values. International cooperation. Global collaboration to create regulations and agreements governing AI research and its applications, aiming to prevent misuse and promote beneficial outcomes. Public engagement, involving diverse stakeholders, including the public, in discussions about AI's future to democratize decision-making and reflect a wide range of perspectives. Navigating the uncharted future. The technological singularity presents a multifaceted paradox, intertwining rapid technological advancement with profound uncertainties. While the pursuit of superintelligent AI holds promise for unprecedented progress, it also necessitates careful consideration of ethical, social, and existential dimensions. By engaging in thoughtful discourse and proactive planning, society can strive to harness the benefits of AI while mitigating potential risks, steering toward a future where technology enhances human flourishing. Imagine if every moment you blinked, the world around you shifted from a haze of endless possibilities to one clear, definite reality. Picture a universe where nothing is fixed until someone, even you, looks at it. It sounds like something out of a science fiction thriller, yet this is the bizarre premise at the heart of the quantum measurement problem. Today, we're diving into a concept that suggests our act of observing could be what gives the universe its shape, turning fuzzy probabilities into the solid reality we experience. At its core, the quantum measurement problem arises from the strange behavior of particles at the quantum level. In the quantum world, particles such as electrons and photons don't exist in a single, determined state. Instead, they reside in a mysterious condition known as superposition, a blend of all possible states at once. Think of it as a cosmic coin spinning in the air, where heads and tails coexist until it finally lands. This peculiar behavior is described by something called the wave function, a mathematical tool that outlines all the possible states of a particle. However, as soon as we measure or observe this particle, the wave function collapses and the particle snaps into one definite state. It's as if the universe holds its breath until we intervene, then it rushes to pick a single, concrete outcome. Consider the famous double-slit experiment. When particles pass through two slits without any observation, they create an interference pattern, proof that they behave like waves. But when we set up detectors to see which slit each particle goes through, the interference pattern vanishes. Suddenly, they act like solid particles following a definite path. This experiment hints at a strange relationship between the act of measurement and the nature of reality itself. Now, let's delve into two of the most talked about interpretations of this phenomenon. The first is the Copenhagen interpretation. This view suggests that the wave function represents our knowledge of a quantum system rather than a physical reality. According to this perspective, the act of measurement forces the system to choose one of the many possibilities, causing the wave function to collapse. It paints a picture of the observer as an almost magical participant who brings the world into clarity simply by looking. On the flip side, we have the many worlds interpretation. This theory boldly claims that every potential outcome of a quantum event actually happens, but in separate, parallel universes. Instead of a wave function collapse, the universe splits into multiple realities, each embodying a different outcome. In this view, our measurement doesn't force a single decision. It just determines which branch of the multiverse we find ourselves in. This idea challenges our traditional view of a single, linear reality, suggesting instead an endless, branching tree of possibilities. Both interpretations offer fascinating insights into the nature of quantum reality, yet they stand in stark opposition. The Copenhagen interpretation emphasizes the mysterious power of observation, suggesting that our very act of looking defines reality. In contrast, the many worlds interpretation minimizes the role of the observer, positing that all outcomes exist simultaneously in an ever-expanding cosmos of parallel universes. In wrapping up our journey through the quantum measurement problem, we are left with an awe-inspiring puzzle that straddles the line between science and philosophy. Whether reality truly hinges on our observation, or if our universe is merely one branch of a vast multiverse, the debate continues to challenge our understanding of existence. What is clear, however, is that the quantum world invites us to question everything we think we know about reality. By exploring these ideas, we not only gain insights into the fabric of the universe, but also learn to appreciate the inherent mysteries that make life so intriguing. In the end, the quantum measurement problem reminds us that the universe might be far more fluid and enigmatic than our everyday experiences suggest, an invitation to continually explore, question, and marvel at the unknown. Imagine watching a film where shattered glass leaps off the floor, reassembling into a perfect window, or where smoke funnels back into a chimney. Such scenes defy our everyday experience, yet the fundamental laws of physics don't explicitly forbid them. This leads us to a profound enigma. Why does time seem to flow inexorably in one direction, from past to future, when theoretically it could just as easily run backward? This is the essence of the arrow of time paradox, a concept that challenges our understanding of reality and the very nature of existence. The term arrow of time was introduced by British astrophysicist Arthur Eddington in 1927 to describe the unidirectional flow of time that we perceive. While the fundamental laws governing microscopic particles are time-symmetric, meaning they don't prefer a forward or backward direction, our macroscopic world exhibits a clear temporal asymmetry. This discrepancy forms the crux of the paradox. One of the most compelling explanations for this phenomenon lies in the second law of thermodynamics, which states that entropy, a measure of disorder in a system, tends to increase over time. In simple terms, natural processes evolve from a state of order to disorder. For instance, a hot beverage cools down as heat dissipates into the surrounding air, and a deck of cards, once shuffled, is unlikely to return to its original ordered state without deliberate intervention. This progression from order to disorder gives rise to the thermodynamic arrow of time, aligning the direction of time with the increase of entropy. However, this explanation raises further questions. If the laws of physics are time-symmetric, why does entropy increase at all? Some physicists propose that the initial conditions of the universe play a pivotal role. They suggest that the universe began in a highly ordered, low-entropy state, a cosmic starting point that set the direction for the arrow of time. As the universe expands and evolves, entropy increases, creating the temporal asymmetry we observe. Yet, not all scientists agree with this perspective. Some argue that our perception of time's flow is a construct of human consciousness, a way for our brains to process and organize information. This viewpoint suggests that the arrow of time is not an inherent feature of the universe, but rather a byproduct of how we experience and interpret reality. The arrow of time paradox invites us to ponder the profound nature of time and our place within it. Whether rooted in the fundamental laws of physics, the initial conditions of the cosmos, or the workings of our consciousness, the unidirectional flow of time remains one of the most intriguing mysteries in science. As we continue to explore this enigma, we not only deepen our understanding of the universe, but also challenge our perceptions of reality, causality, and existence itself. Imagine gazing up at the night sky, each twinkling star potentially hosting planets teeming with life. With billions of stars in our galaxy alone, it's statistically probable that intelligent civilizations should exist elsewhere. Yet, despite our best efforts, we find ourselves in a profound silence. This puzzling contradiction between the high likelihood of extraterrestrial intelligence and the lack of evidence for its existence is known as the Fermi Paradox, a question that challenges our understanding of our place in the cosmos. The Fermi Paradox is named after physicist Enrico Fermi, who famously asked, "Where is everybody?" The paradox arises from two observations. The vastness of the universe suggests that intelligent life should be common, yet we have no definitive proof of such life beyond Earth. This discrepancy has led to numerous hypotheses attempting to explain the silence. One prominent explanation is the concept of the Great Filter, which suggests that there is a stage in the evolutionary timeline that is extremely difficult for life to surpass. This filter could be behind us, implying that the emergence of intelligent life is rare, or ahead of us, indicating that advanced civilizations tend to self-destruct before achieving interstellar communication. The Great Filter thus presents a sobering perspective on the longevity of technological societies. Another consideration is the possibility that advanced civilizations are utilizing communication methods beyond our current technological capabilities. While humanity primarily searches for radio signals, extraterrestrial societies might employ more sophisticated means, such as neutrino-based communication or quantum entanglement, rendering their messages undetectable by our instruments. The zoo hypothesis offers a different angle, proposing that advanced civilizations intentionally avoid contact with us to allow for natural evolution and socio-cultural development, much like zookeepers observing animals without interference. This perspective suggests that Earth is part of a cosmic preserve, shielded from interaction until we reach a certain level of maturity or technological prowess. Alternatively, the planetarium hypothesis posits that our perception of the universe is a carefully crafted illusion designed to appear empty of other life. In this scenario, advanced beings have created a simulated reality for us, and the true nature of the cosmos, including the existence of other civilizations, remains hidden behind this facade. Some theories suggest that extraterrestrial civilizations are indeed out there, but are simply uninterested in communication or exploration. They may be content with their own environments, lacking the curiosity or motivation to seek out other life forms. Additionally, the vast distances between stars present significant challenges for interstellar travel and communication, potentially leading civilizations to focus inward rather than outward. The Fermi Paradox encapsulates the profound mystery of our solitude in the vast expanse of space. Whether the silence signifies the rarity of intelligent life, the limitations of our detection methods, or the presence of insurmountable barriers, it compels us to reflect on our own civilization's trajectory and the future of our exploration efforts. As we continue to scan the cosmos for signs of life, the paradox serves as a humbling reminder of the challenges inherent in our quest to understand our place in the universe. Ball lightning paradox. Defining ball lightning. Ball lightning is a rare and enigmatic atmospheric phenomenon characterized by luminous, spherical objects that appear during thunderstorms. These orbs vary in size, color, and behavior, often described as drifting through the air before dissipating or exploding. Despite numerous eyewitness accounts, ball lightning remains poorly understood, posing significant challenges to scientists seeking to explain its nature and origins. Exploring observations, theories, and scientific investigations. Documented observations. Throughout history, ball lightning has been reported worldwide, with descriptions noting their sudden appearance, floating motion, and transient existence. Witnesses often observe these spheres during or after thunderstorms, with colors ranging from white and yellow to red and blue. Some accounts detail the balls moving through windows or confined spaces, adding to the mystery of their behavior. Proposed scientific explanations. Several hypotheses have been proposed to explain ball lightning, though none have achieved widespread acceptance. Vaporized silicon hypothesis. This theory suggests that ball lightning results from lightning strikes vaporizing soil, producing silicon vapor that condenses into glowing spheres. Spectral analyses have detected silicon-related emissions in ball lightning observations, lending some support to this idea. Plasma oscillation model. Proposed by some researchers, this model posits that ball lightning consists of a plasma sphere stabilized by electromagnetic fields, allowing it to persist longer than typical lightning phenomena. Magnetic field-induced hallucination. Some scientists speculate that ball lightning might be a visual hallucination induced by the intense magnetic fields produced by nearby lightning, affecting the visual cortex of the brain. However, this theory does not account for physical interactions observed with ball lightning, such as their movement and impact on objects. Scientific investigations and challenges. The elusive nature of ball lightning has made it difficult to study under controlled conditions. Laboratory recreations have attempted to mimic the phenomenon, but results have been inconsistent, and the observed effects often differ from eyewitness reports. In 2014, researchers captured the first optical spectrum of natural ball lightning, providing valuable data on its composition and behavior. However, much remains unknown about its underlying physics. Theoretical perspectives. Some scholars suggest that existing scientific concepts may be insufficient to fully understand ball lightning, proposing the need for new theories or models. The concept of a parallel space has been introduced as a potential framework to explain the unique properties of ball lightning, though this remains speculative and unproven. The ongoing mystery. Ball lightning continues to intrigue and puzzle scientists and enthusiasts alike. Despite numerous theories and occasional empirical data, a comprehensive understanding of this phenomenon remains elusive. Continued research, technological advancements, and perhaps serendipitous observations may eventually shed light on the true nature of ball lightning, transforming it from a mysterious curiosity into a well-understood aspect of atmospheric science. Baryogenesis Paradox. Understanding the matter-antimatter imbalance. The universe exhibits a striking imbalance between matter and antimatter, with observable matter vastly outweighing antimatter. This disparity is encapsulated in the baryon asymmetry problem, which seeks to explain why the cosmos is predominantly composed of matter. The prevailing hypothesis to address this issue is baryogenesis, aiming to elucidate the mechanisms that led to the observed matter-antimatter asymmetry. Exploring the foundations and challenges of baryogenesis. Sakharov's conditions for baryogenesis. In 1967, physicist Andrei Sakharov outlined 3 essential conditions that any theory of baryogenesis must satisfy to account for the matter-antimatter imbalance. Baryon number violation. Processes that violate the conservation of baryon number are crucial for generating an excess of baryons over antibaryons. While certain non-perturbative interactions in the Standard Model may violate baryon number, significant baryon number violation is not observed experimentally, suggesting the need for new physics beyond the Standard Model. C and CP symmetry violation. Charge C and charge parity, CP. Symmetry violations are necessary to distinguish between matter and antimatter interactions. Although CP violation has been observed in weak interactions, the observed amount is insufficient to account for the baryon asymmetry, indicating that additional sources of CP violation are likely present in the universe. Departure from thermal equilibrium. For baryogenesis to occur, interactions must happen out of thermal equilibrium, preventing the system from reaching a state where matter and antimatter are produced in equal amounts. This condition ensures that processes generating baryon asymmetry are not undone by subsequent thermal processes. Challenges and open questions. Despite the theoretical framework provided by Sakharov's conditions, several challenges persist in understanding baryogenesis. Absence of observed baryon number violation. Experimental searches for processes that violate baryon number conservation, such as proton decay, have not yielded definitive evidence, leaving a gap between theoretical predictions and experimental observations. Insufficient CP violation. The amount of CP violation observed in current experiments falls short of what is needed to explain the observed baryon asymmetry, suggesting that new sources of CP violation await discovery. Out of equilibrium conditions. While certain high-energy processes in the early universe could have provided the necessary out-of-equilibrium conditions, the specifics of these processes remain uncertain and are subject of ongoing research. Alternative theories and ongoing research. Researchers continue to explore various mechanisms and extensions to the Standard Model to address the baryon asymmetry. Leptogenesis. This theory posits that the matter-antimatter asymmetry originated from lepton number-violating processes, which subsequently led to baryon asymmetry through interactions that link lepton and baryon numbers. Baryogenesis through primordial black holes. Some hypotheses suggest that interactions involving primordial black holes could have contributed to the baryon asymmetry, though this remains a speculative area of research. Mirror twin Higgs models. These models propose that the universe contains a mirror sector with identical particles but opposite parity, offering potential explanations for baryogenesis through asymmetric reheating processes. The quest for understanding baryogenesis. Baryogenesis remains one of the most profound puzzles in cosmology and particle physics, challenging our understanding of the fundamental laws governing the universe. While significant progress has been made in formulating theoretical models and conducting experiments, a comprehensive understanding of the mechanisms that led to the matter-dominated universe we observe today continues to elude scientists. Ongoing research and future experiments are crucial to unraveling this cosmic mystery. The cuspy halo problem. The dark matter enigma. Dark matter, an unseen form of matter that does not emit or absorb light, is believed to constitute about 27% of the universe's mass energy content. Its existence is inferred from gravitational effects on visible matter, radiation, and the large-scale structure of the universe. However, the exact nature of dark matter remains one of the most profound mysteries in cosmology and particle physics. Theoretical predictions versus observational evidence. Theoretical predictions, cuspy density profiles. In the framework of the cold dark matter (CDM) model, which posits that dark matter consists of slow-moving, non-relativistic particles, cosmological simulations predict that dark matter halos, the gravitational wells that surround galaxies, should exhibit a cuspy density profile. This means that the dark matter density increases steeply toward the center of these halos, following a power law distribution with an index between -1 and -1.5. Such profiles suggest a high concentration of dark matter near galactic centers. Observational evidence, core density profiles. Contrastingly, observations of low-mass galaxies reveal a different picture. The rotation curves of these galaxies, graphs plotting the orbital velocities of stars and gas against their radial distance from the galactic center, indicate that the dark matter density remains relatively flat or cored in the central regions. This observation implies a more uniform distribution of dark matter near the core, rather than the steep increase predicted by CDM simulations. The core cusp discrepancy. This discrepancy between the predicted cuspy profiles and the observed core profiles is known as the core cusp problem. It challenges the standard CDM paradigm, suggesting that our understanding of dark matter behavior on galactic scales may be incomplete. Wikipedia. Proposed solutions and ongoing research. Baryonic feedback mechanisms. One leading explanation for the core cusp problem involves baryonic feedback processes, such as those driven by supernovae and active galactic nuclei. These energetic events can expel gas from the central regions of galaxies, altering the gravitational potential and leading to the transformation of cuspy dark matter profiles into cored ones. Simulations incorporating these feedback mechanisms have shown promise in reproducing the observed flat central densities. Alternative dark matter models. Beyond modifications to baryonic physics, researchers are exploring alternative dark matter models to address the core cusp problem. For instance, theories involving warm dark matter, which consists of particles with velocities higher than those in the CDM model, predict a suppression of small-scale structures. This suppression could lead to the formation of core density profiles in dark matter halos, aligning better with observational data. Numerical simulation improvements. Some scientists propose that the discrepancies might arise from numerical artifacts in cosmological simulations. Issues such as insufficient resolution or inadequate modeling of physical processes could lead to the emergence of artificial cuspy profiles. Enhancing the accuracy and resolution of these simulations is considered crucial for resolving the core cusp issue. Advancing our understanding of dark matter. The core cusp problem remains a significant puzzle in cosmology, prompting ongoing research into both observational techniques and theoretical models. Addressing this issue is vital for refining our understanding of dark matter's role in galaxy formation and evolution. Continued observations, coupled with advanced simulations and novel theoretical frameworks, are essential steps toward resolving the discrepancies between theory and observation in dark matter research. Arrow's impossibility theorem, also known as social choice paradox. The essence of the theorem. Formulated by economist Kenneth Arrow in his 1951 book Social Choice and Individual Values, Arrow's impossibility theorem presents a fundamental challenge in the field of social choice theory. It asserts that no rank-order voting system can simultaneously fulfill a specified set of seemingly reasonable criteria when aggregating individual preferences into a collective decision. This result highlights inherent limitations in designing fair and rational voting mechanisms. Delving deeper into the theorem. The core criteria. Fairness in voting systems. Arrow identified several conditions that a fair voting system should satisfy. Unrestricted domain, universality. Every possible set of individual preferences should be allowed. Non-dictatorship. No single voter should have the power to always determine the group's preference. Parado efficiency unanimity. If every voter prefers one option over another, the group's preference should reflect this. Independence of irrelevant alternatives. III. The group's preference between two options should not be affected by the introduction of a third, irrelevant option. Non-imposition. Citizen sovereignty. Every possible societal preference order should be achievable, given some set of individual preferences. Arrow's theorem demonstrates that no voting system can satisfy all these conditions simultaneously when there are three or more options to choose from. This result implies that compromises are inevitable in any voting system, and some degree of fairness may be unattainable. Intuitive illustration, the voting paradox. Consider a scenario with three candidates, A, B, and C, and three voters with the following preferences. Voter 1 prefers A greater than B greater than C. Voter 2 prefers B greater than C greater than A. Voter 3 prefers C greater than A greater than B. Applying a majority rule to each pair of candidates leads to cyclical preferences. A is preferred over B. Voters 1 and 3 prefer A to B. B is preferred over C. Voters 1 and 2 prefer B to C. C is preferred over A. Voters 2 and 3 prefer C to A. This cycle A greater than B greater than C greater than A reveals a collective preference that is intransitive, challenging the notion of a clear societal choice. Implications for voting systems. Arrow's theorem has profound implications for the design of voting systems. Plurality systems. Systems like first-past-the-post often fail to meet fairness criteria, as they can lead to results that don't reflect the true preferences of the majority. Ranked choice voting. While aiming to address some issues, ranked choice methods are also susceptible to paradoxes highlighted by Arrow's theorem. Condorcet methods. These methods seek to identify a candidate who would win against every other candidate in head-to-head comparisons. However, they can result in cyclical preferences, similar to the example above. Beyond voting, broader applications. Arrow's theorem extends beyond electoral systems, influencing areas like collective decision-making in organizations and committees. Aggregating individual preferences into a group decision can be fraught with inconsistencies. Economic theory, understanding how individual preferences translate into market choices and social welfare considerations. Philosophy and ethics, debates about the nature of collective judgment and the challenges in achieving a fair consensus. Embracing the paradox. Arrow's impossibility theorem serves as a sobering reminder of the complexities inherent in collective decision-making. It underscores the challenges in designing systems that are simultaneously fair, rational, and representative of diverse individual preferences. Recognizing these limitations encourages ongoing exploration of alternative decision-making frameworks and a deeper understanding of the trade-offs involved in collective choices. Color confinement, the enigma of the strong force. The strong interaction and quantum chromodynamics. In the realm of particle physics, the strong interaction is the fundamental force responsible for binding quarks together to form protons, neutrons, and other hadrons. This interaction is described by quantum chromodynamics (QCD), a theory that explains how quarks and gluons, the force carriers of the strong force, interact with one another. A pivotal concept within QCD is color confinement, which posits that quarks and gluons are never found in isolation under normal conditions. Understanding color confinement. The nature of color charge. In QCD, quarks and gluons possess a type of charge known as color charge, which comes in three types: red, green, and blue for quarks, and corresponding anticolors for antiquarks. This terminology is purely symbolic, with no relation to actual colors, and serves to distinguish the types of charge involved in strong interactions. Mechanism of confinement. The phenomenon of color confinement arises from unique properties of the strong force. Force behavior with separation. Unlike the electromagnetic force, which weakens with distance, the strong force between quarks remains constant or even intensifies as they are separated. This results in the formation of a narrow flux tube, or string, connecting the quarks. Energy considerations. As quarks are pulled apart, the energy invested in stretching the flux tube increases. At a certain point, it becomes energetically favorable for the energy to materialize into a new quark-antiquark pair, leading to the creation of additional hadrons rather than isolating a single quark. Consequences of confinement. Due to color confinement. Hadron formation. Quarks are permanently confined within hadrons, combinations of quarks that are color neutral. The most common hadrons are baryons, composed of 3 quarks, and mesons, composed of a quark and an antiquark. Experimental observations. High-energy experiments that attempt to separate quarks result in the production of new quark-antiquark pairs, leading to jets of particles rather than isolated quarks. This behavior aligns with the concept of hadronization, where quarks transition into hadrons. Theoretical challenges. Despite its empirical success, color confinement remains a theoretical challenge. Lack of analytical proof. There is no rigorous analytical proof of confinement within non-abelian gauge theories like QCD. The non-perturbative nature of confinement makes it difficult to study using traditional analytical methods. Numerical simulations. Researchers employ lattice QCD simulations to study confinement, discretizing spacetime into a lattice to make the problem computationally tractable. These simulations provide insights but are limited by computational resources and the complexity of the interactions involved. The ongoing quest to unveil confinement. Color confinement is a fundamental aspect of the strong interaction, ensuring that quarks and gluons are never observed as free particles. While the phenomenon is well supported by experimental evidence, a comprehensive theoretical understanding remains elusive. Advancements in computational techniques and experimental observations continue to shed light on this complex aspect of particle physics, bringing scientists closer to unraveling one of the most intriguing mysteries of the subatomic world. Baryon asymmetry. A universe dominated by matter. The universe we observe today is made up predominantly of matter, yet the laws of physics suggest that matter and antimatter should have been created in equal amounts during the Big Bang. However, this symmetry has not been observed in our cosmos. Instead, an imbalance, known as baryon asymmetry, exists with far more matter than antimatter, leading to the question, where did all the antimatter go? The origins of baryon asymmetry. Theoretical foundations. Sakharov's conditions. In 1967, Russian physicist Andrei Sakharov proposed a set of conditions that any theory of baryon asymmetry must satisfy. These include baryon number violation. Processes must occur that violate the conservation of baryon number to create an imbalance between matter and antimatter. C and CP violation. Charge C and charge parity, CP. Symmetry violations are required to distinguish between matter and antimatter. Departure from thermal equilibrium. The system must be out of thermal equilibrium to prevent the annihilation of matter and antimatter from reaching a balanced state. Existing mechanisms for baryon asymmetry. Several mechanisms have been proposed to explain the baryon asymmetry, all of which must incorporate these conditions. Here are some of the most well-known ideas. Electroweak baryogenesis. This theory suggests that baryon asymmetry could have emerged during the electroweak phase transition in the early universe when the weak nuclear force and electromagnetic force separated. This process could have violated baryon number conservation and produced a baryon asymmetry. Leptogenesis. Leptogenesis posits that the imbalance in leptons, such as electrons and neutrinos, during the early universe ultimately led to baryon asymmetry through interactions between leptons and quarks. Affleck-Dine mechanism. In this scenario, scalar fields in the early universe decay into particles, leading to a violation of baryon number and the generation of an imbalance between matter and antimatter. Strong dynamics and phase transitions. Some theories suggest that strong interactions during phase transitions in the early universe could have played a role in producing baryon asymmetry. The strong force, which governs the interactions between quarks and gluons, might have influenced baryon production in ways not yet fully understood. Experimental challenges. While various models for baryon asymmetry exist, none have been definitively proven. Experimental evidence for processes like baryon number violation is still lacking. Particle detectors have not observed proton decay, and the expected amount of CP violation in the standard model is too small to explain the observed matter-antimatter imbalance. Cosmological observations and evidence. Cosmological observations, particularly those related to the cosmic microwave background, CMB, provide some evidence for baryon asymmetry. The distribution of galaxies and large-scale structures in the universe also reflects the dominance of matter over antimatter. In addition, the matter-antimatter imbalance is required to explain the existence of galaxies, stars, and planets as we know them. Without such an imbalance, matter would have been annihilated by antimatter in the early universe, leaving only radiation behind. The quest to understand baryon asymmetry. The problem of baryon asymmetry is one of the most fundamental questions in cosmology and particle physics. While many theoretical frameworks attempt to explain how this imbalance occurred, scientists are still working to confirm which of these theories best describes the early universe's conditions. Addressing this mystery will not only deepen our understanding of the universe's origins, but also provide insights into the unification of fundamental forces and the nature of particle interactions in the extreme conditions of the early cosmos. Cosmic coincidence. The enigmatic coincidences of the cosmos. Throughout the universe, certain phenomena appear to align in ways that seem improbable, leading to what are known as cosmic coincidences. These coincidences often provoke contemplation about the underlying principles governing the cosmos and our place within it. Exploring notable cosmic coincidences. 1. The coincidence of dark matter and dark energy densities. In cosmology, the cosmic coincidence refers to the observation that the energy densities of dark matter and dark energy are of the same order of magnitude at the present epoch. Dark matter, which exerts a gravitational pull, tends to slow down the universe's expansion, while dark energy, a form of repulsive energy, accelerates it. The fact that these opposing influences are comparable in strength now, despite having vastly different effects on the universe's dynamics, presents a puzzling scenario for cosmologists. 2. The serendipity of solar eclipses. From our vantage point on Earth, the Sun and the Moon appear to be nearly the same size in the sky, allowing for the phenomenon of total solar eclipses. This is due to a remarkable coincidence. The Sun's diameter is approximately 400 times larger than that of the Moon, and it is also about 400 times farther away from Earth. This unique alignment enables the Moon to cover the Sun's disk completely during an eclipse, creating a spectacular celestial event. 3. The synchronization of Earth's orbit and seasonal climates. Another intriguing coincidence lies in Earth's orbital dynamics. The planet reaches its closest point to the Sun, known as perihelion, in early January, coinciding with the peak of the Southern Hemisphere's summer. This alignment results in the Southern Hemisphere receiving slightly more solar energy during this period, influencing seasonal climate patterns. 4. The apparent coincidence of the Hubble constant. Recent observations by the James Webb Space Telescope have confirmed that the universe is expanding at a rate about 8% faster than previously expected, a discrepancy known as the Hubble tension. This finding suggests a gap in our current understanding of the universe, particularly concerning dark matter, dark energy, and gravity. Researchers are now tasked with revising existing models to account for this unexpected expansion rate. Reflecting on the nature of cosmic coincidences. These cosmic coincidences invite us to ponder the fundamental laws and constants that shape our universe. While some may be dismissed as statistical anomalies, others challenge our scientific models, prompting deeper inquiry into the nature of reality. As our observational and analytical tools advance, we continue to uncover the intricate tapestry of coincidences that define the cosmos, enhancing our understanding of the universe and our place within it. The Krill Paradox, unraveling the impact of whales on krill populations. The enigma of the krill paradox. The Southern Ocean encircling Antarctica has long been the setting for a perplexing phenomenon known as the krill paradox. This paradox highlights the unexpected decline in krill populations despite a significant reduction in their primary predators, the baleen whales, due to commercial whaling. Intuitively, one might expect that fewer whales would lead to an increase in krill numbers. However, observations suggest otherwise. Exploring the dynamics of the krill paradox. The role of whales in the marine ecosystem. Baleen whales play a crucial role in the marine food web, not only as predators, but also as contributors to the health of krill populations. Whale consumption. Large whales are significant consumers of krill. Recent studies have revealed that these whales consume at least 3 times more krill than previously estimated, underscoring their impact on krill populations. Nutrient recycling. Beyond predation, whales contribute to the marine ecosystem through their feces, which fertilize phytoplankton, the primary food source for krill. This process enhances primary productivity, supporting a healthy krill population. The impact of commercial whaling. The extensive hunting of whales during the 20th century led to a dramatic decrease in whale populations. This reduction had several unforeseen consequences. Decreased nutrient input. With fewer whales, there was a decline in whale feces, leading to reduced fertilization of phytoplankton. This decrease in primary productivity adversely affected krill populations as their food source diminished. Alter marine dynamics. The removal of whales disrupted the balance of the marine ecosystem, leading to changes that favored other krill predators, such as seals, seabirds, and fish. However, these predators did not compensate for the loss of whale predation, resulting in an overall decline in krill numbers. Recent developments and ongoing concerns. The krill paradox remains a pressing issue, especially in light of current events. Increased krill fishing. Recent reports indicate a significant rise in krill fishing, with 498,000 metric tons harvested in the past year. This surge raises concerns about the sustainability of krill populations and the broader implications for the marine food web. Geopolitical challenges. Efforts to establish fishing restrictions and marine protected areas in Antarctica face opposition from countries like China and Russia. Their vetoes have hindered conservation initiatives, posing risks to the delicate balance of the Antarctic ecosystem. Addressing the complexity of the krill paradox. The krill paradox underscores the intricate interdependencies within marine ecosystems. It highlights how the decline of a single species, such as the whale, can have cascading effects on the entire food web, ultimately impacting the very populations that were seemingly unaffected. Addressing this paradox requires a holistic approach to marine conservation, considering the multifaceted roles that species play and the far-reaching consequences of human activities. The paradox of the plankton. The enigma of plankton diversity. In aquatic environments, an astonishing variety of plankton species coexist, each vying for a limited array of resources. This observation presents a conundrum known as the paradox of the plankton, which challenges traditional ecological principles. Unpacking the paradox. The competitive exclusion principle. The competitive exclusion principle posits that when multiple species compete for identical resources, one will inevitably outcompete the others, leading to the extinction of the less competitive species. This principle suggests that only a few species should thrive in such competitive conditions. Observe plankton diversity. Contrary to this principle, aquatic ecosystems teem with a multitude of plankton species, all seemingly competing for the same limited resources. This disparity between theory and observation forms the essence of the paradox. Proposed explanations. Researchers have proposed several hypotheses to resolve this paradox. Spatial and temporal heterogeneity. Variations in environmental conditions, such as light availability and nutrient concentrations, create diverse niches that different plankton species can exploit at various times and locations. Microhabitat differentiation. Even in seemingly uniform environments, subtle differences in microhabitats allow species to specialize and coexist. Predation pressure. Predators can influence plankton populations, preventing any single species from dominating and thus maintaining diversity. Viral interactions. Viruses can regulate plankton populations by infecting and lysing host cells, thereby controlling the abundance of certain species and promoting diversity. Individual variability. Variations within species, such as differences in behavior or physiology, can reduce direct competition and facilitate coexistence. Embracing complexity in plankton communities. The paradox of the plankton underscores the complexity of aquatic ecosystems, where multiple factors interplay to sustain high levels of biodiversity. Understanding these mechanisms is crucial for comprehending ecological dynamics and the resilience of marine environments. The Sorites Paradox, also known as the paradox of the heap, delves into the complexities arising from vague predicates, terms without clear-cut boundaries. Originating from ancient philosophical discourse, this paradox challenges our understanding of concepts that lack precise definitions. Deconstructing the paradox. Understanding the Sorites paradox. The term Sorites is derived from the Greek word for heap. The paradox typically unfolds through a scenario involving a heap of sand. Starting point. Begin with a heap of sand consisting of, say, 1 million grains. Gradual reduction. Remove grains one at a time. The question. At what point does the collection cease to be considered a heap? Intuitively, removing a single grain doesn't seem to change the status of being a heap. However, after successive removals, we face the question, at what exact number does it stop being a heap? This dilemma exposes the challenges in applying vague terms to real-world situations. Real-world examples of vagueness. Beyond heaps of sand, vagueness permeates everyday language and concepts. Baldness. At what point does a person transition from being not bald to bald? Tallness. How tall must one be to be considered tall? Aging. When does someone become old? These examples underscore the absence of clear-cut boundaries in many classifications we routinely make. Philosophical and logical implications. The Sorites Paradox invites deep philosophical inquiry into the nature of concepts and language. Continuum problem. It highlights the difficulty in drawing precise lines within continuous spectra. Epistemic uncertainty. The paradox challenges our knowledge about when and how vague predicates apply. Logical frameworks. Traditional binary logic struggles with the gray areas presented by vague terms, prompting the exploration of alternative logical systems. Proposed resolutions. Various approaches have been proposed to address the challenges posed by the Sorites paradox. Fixed boundary approach. Establishing a specific threshold, e.g., a heap requires at least 100 grains to delineate when a term applies. However, this method is often criticized for its arbitrariness. Epistemicism, suggesting that there are precise boundaries, but they are unknowable, thus embracing the inherent vagueness without attempting to eliminate it. Multi-valued logic, introducing systems where truth values are not limited to true or false, but include degrees of truth to better capture the nuances of vague predicates. Group consensus, determining the application of vague terms based on collective agreement or societal usage, acknowledging that meanings can be fluid and context-dependent. Practical applications and implications. The Sorites Paradox extends beyond theoretical discussions, influencing various practical domains. In economics, for instance, it challenges the analysis of consumer preferences, especially when individuals exhibit indifference between quantities that differ minutely. This scenario complicates the establishment of precise thresholds for decision-making and policy formulation. Similarly, in legal and ethical debates, such as those surrounding abortion, the paradox highlights difficulties in defining exact points where moral or legal statuses change, given the continuum of development. These real-world applications underscore the pervasive nature of the Sorites paradox, prompting ongoing discussions about how to handle concepts that resist clear-cut definitions. The Sorites paradox serves as a poignant reminder of the complexities inherent in human language and cognition. It challenges us to confront the limitations of our conceptual frameworks and encourages the development of more nuanced approaches to understanding and communicating about the world around us. The Blue Paradox, navigating the dual nature of plastic in our oceans. The dichotomy of plastic in marine environments. Plastics have revolutionized industries and daily life through their versatility and convenience. However, their pervasive presence in marine ecosystems has led to the emergence of the Blue Paradox, a term that encapsulates the conflicting roles of plastic as both a catalyst for human progress and a significant environmental threat. Understanding the Blue Paradox. Plastic as a catalyst for human advancement. Plastics have been instrumental in various sectors, including medical innovations. Disposable syringes for bags and various life-saving devices are crafted from medical-grade plastics, ensuring sterility and reducing the risk of infection. Technological progress. Lightweight and durable plastic components are fundamental in the manufacturing of electronic devices, from smartphones to computers, enhancing functionality and portability. Economic growth. The plastic industry provides employment opportunities globally, supporting economies through the production and distribution of a vast array of plastic products. Agricultural efficiency. Plastic materials are used in greenhouses, irrigation systems, and packaging, contributing to increased agricultural productivity and food preservation. Transportation safety. Automobiles and aircraft utilize plastic components to reduce weight, improve fuel efficiency, and enhance passenger safety through features like airbags and seatbelts. Plastic as an environmental menace. Conversely, the durability and low cost of plastics have led to their widespread, often irresponsible, use and disposal, resulting in marine pollution. Millions of tons of plastic enter the oceans annually, leading to the formation of massive garbage patches, such as the Great Pacific Garbage Patch. Harm to marine life. Ingestion and entanglement of marine organisms in plastic debris cause injuries, fatalities, and disruptions to marine food chains. Ecosystem disruption. The degradation of plastics releases toxic substances into marine environments, affecting water quality and the health of aquatic ecosystems. Microplastics contamination. Tiny plastic particles are ingested by marine organisms, entering the food chain and potentially impacting human health. Economic impact on fisheries. Fishing industries suffer losses due to the decline in fish populations and the costs associated with cleaning up plastic debris. Aesthetic degradation. Beaches and coastlines littered with plastic waste deter tourism and diminish natural beauty. Addressing the Blue Paradox. To reconcile the benefits and detriments of plastic, a multifaceted approach is essential. Innovative design. Developing biodegradable or recyclable plastics can reduce long-term environmental impact. Enhanced waste management. Implementing efficient waste collection, recycling, and disposal systems to prevent plastic leakage into marine environments. Public awareness. educating consumers and industries about the environmental impacts of plastic waste to foster responsible usage and disposal practices. Policy implementation. Governments can enact regulations and incentives to reduce single-use plastic production and consumption, promoting sustainable alternatives. Corporate responsibility. Encouraging companies to adopt sustainable packaging solutions and take accountability for the life cycle of their products. Community engagement, organizing local cleanup efforts and supporting grassroots initiatives to address plastic pollution at the community level. Scientific research, investing in research to develop new materials and technologies that minimize environmental harm. International collaboration, participating in global treaties and agreements aimed at reducing plastic waste and protecting marine environments. Navigating towards a sustainable future. The Blue Paradox challenges society to balance the undeniable advantages of plastics with their potential to harm marine ecosystems. Through collaborative efforts in innovation, waste management, education, and policymaking, it is possible to mitigate the adverse effects of plastic pollution while retaining the benefits that plastics offer. Louville's Paradox, the enigma of phase-space volume conservation. The puzzle of Louville's theorem. In classical mechanics, Louville's theorem asserts that the phase-space volume occupied by a system of particles remains constant over time, provided the system evolves according to Hamiltonian dynamics. This implies that the density of system points in phase space is preserved as the system evolves. Delving deeper into Louville's theorem, understanding phase space and its significance. Phase space is a multidimensional space in which all possible states of a system are represented, with each state corresponding to one unique point in the phase space. For a single particle, this space is six-dimensional, comprising 3 position coordinates and 3 momentum coordinates. Louville's theorem implies that as the system evolves, the volume of any region in this phase space remains unchanged, ensuring the preservation of the system's statistical properties over time. Mathematical formulation of Louville's theorem. Mathematically, Louville's theorem arises from the fact that the divergence of the Hamiltonian vector field vanishes. Implications and applications. Statistical mechanics. Louville's theorem underpins the foundation of statistical mechanics, ensuring that the statistical properties derived from phase space averages are time invariant for isolated systems. Deterministic chaos. In systems exhibiting chaotic behavior, while individual trajectories may appear random, the overall distribution of trajectories remains uniform in phase space due to Louville's theorem. Quantum mechanics transition. Louville's theorem provides a bridge between classical and quantum descriptions, with its principles influencing the development of quantum statistical mechanics. Reconciling with the arrow of time. While Louville's theorem ensures the conservation of phase-space volume in deterministic, reversible dynamics, it presents a conceptual challenge when juxtaposed with the apparent irreversibility observed in macroscopic systems, as encapsulated by the second law of thermodynamics. This juxtaposition invites deeper exploration into the foundations of statistical mechanics and the emergence of macroscopic irreversibility from microscopic reversibility.